Exploring Nothingness, A Journey Through Space and Time. Ayoub Lafriki. I started thinking about this book while I had nothing. No freedom, no space, just time and thought. Ayoub Lafriki. Contents. Cover. Title page. Introduction. Chapter 1, Origins of the Universe. Chapter 2, The Architecture of the Cosmos. Chapter 3, Time, the Fourth Dimension. Chapter 4, The Life and Death of Stars. Chapter 5, Black Holes and Beyond. Chapter 6, Gravity and the Fabric of Spacetime. Chapter 7, Parallel Realities and the Expanding Universe. Chapter 8, Life in the Cosmos. Chapter 9, Humanity's Journey to the Stars. Chapter 10, The Illusion of Nothingness. Chapter 11, The Eternal Journey. Albert Einstein, Stephan Hawking. Glossary. About the author. Introduction. The universe is not just a place, it is a story, a symphony of existence unfolding across dimensions we are only beginning to understand. From the first unfathomable instant when time itself ignited, to the ever-expanding fabric of galaxies strewn across the void, the cosmos invites us to ask questions that reach beyond science into the deepest corners of philosophy and imagination. This book, Exploring Nothingness, A Journey Through Space and Time, is a voyage into that grand story. It is not merely a presentation of facts, but a quest to illuminate the profound interconnectedness of all things, from the tiniest quantum fluctuations to the colossal arcs of galactic superclusters. It is a journey both outward into the vastness of space and inward into the mysteries of time, gravity, life, and consciousness itself. Each chapter will serve as a step on this path. Beginning with the origins of the universe, we will trace the architecture of the cosmos, dive into the strange nature of time, witness the life cycles of stars, and venture into the enigmas of black holes. We will explore gravity as the weaver of the cosmic tapestry, contemplate the expansion of reality itself into parallel realms, and search for life beyond our pale blue dot. We will reflect on humanity's bold steps into the stars and wrestle with the paradoxical notion of nothingness, before ultimately arriving at an eternal, ever-unfolding journey, a journey we are part of. Today, astonishingly, we find ourselves at the threshold of possibilities once reserved for the realm of science fiction. In recent acknowledgments, even the White House in its remarks at the Endless Frontiers retreat on April 14, 2025 has noted that technologies capable of manipulating space and time are not just theoretical but are actively being explored. Our technologies permit us to manipulate time and space. They leave distance annihilated, cause things to grow, and improve productivity. The idea that humanity may one day bend spacetime itself, once a dream confined to the pages of speculative fiction, is slowly becoming part of our scientific frontier. My goal is to blend the known with the unknown, the scientific with the philosophical, the observable with the imaginable. Along the way, you will find moments where certainty gives way to wonder, and where wonder itself becomes the guiding light. I invite you to join me, not simply as a reader, but as a fellow explorer, as we embark together on this endless, exhilarating voyage through space and time. The cosmos awaits. Chapter 1. Origins of the Universe. Before time had a name, before stars lit the darkness, before matter found form, there was nothing. But nothing, as it turns out, is not empty. This paradox lies at the heart of modern cosmology and sets the stage for our journey. In the silence before creation, the universe awaited its first breath, not in the way lungs draw air, but in the sudden, unfathomable expansion we now call the Big Bang. Not a bang in sound, but a burst of being. From a singularity smaller than a grain of sand, space and time erupted, unfolding dimensions, birthing energy, mass, and motion, and the very laws that would govern them. In mere moments, less than a fraction of a second, cosmic inflation drove the universe to expand faster than the speed of light, smoothing out irregularities and setting the stage for structure. Quarks combined into protons and neutrons, photons decoupled from matter, and the universe cooled, dimming from a white-hot brilliance to a deep, expanding void, peppered with the seeds of galaxies. But this chapter of origin is also a chapter of contradiction. If everything began from something infinitesimally small, where did that something come from? And what of the nothing before it? Was it truly nothing, or something beyond the reach of our instruments, our equations, our imaginations? This is where science meets philosophy, and where my research into nothingness might offer a bridge. Could it be that what we perceive as nothing is in fact a dynamic field, a quantum potential, a stage of latent realities not yet actualized? In the emptiness before the cosmos, quantum fluctuations danced. Tiny perturbations, virtual particles appearing and vanishing in less than the blink of an eye, foreshadowed structure and substance. From this strange vacuum, where uncertainty rules and probability is law, came the seeds of everything. As the newborn universe expanded and cooled, it entered an age of primordial simplicity. For the first 380,000 years, it was a seething soup of subatomic particles, too hot and too dense for atoms to form. Photons, the carriers of light, collided relentlessly with electrons and protons, trapped in a blinding fog. Then came recombination. In this moment, electrons paired with protons to form the first atoms, mostly hydrogen, with traces of helium. Freed from the chaos, photons began to travel unimpeded across space, leaving behind a ghostly afterglow known today as the cosmic microwave background, CMB. This faint radiation, still detectable, is a snapshot of the infant universe, a map of the oldest light in existence. From these humble beginnings, structure began to emerge. Over millions of years, gravity, the quiet sculptor of the cosmos, pulled atoms together into clouds, then into stars, galaxies, and clusters. The universe became hierarchical, organizing itself in patterns echoing fractals, from solar systems to galactic filaments, all woven into a cosmic web. But while we trace the unfolding of complexity, a deeper question persists: what came before? Modern physics is remarkably good at describing the evolution of the universe from the first trillionth of a second onward. But at the very origin, t=0, our theories falter. General relativity predicts a singularity, an infinite density where space and time break down. Quantum mechanics, on the other hand, offers no clear resolution. The laws that govern the small and the vast cannot yet be unified. And here, we turn to a notion that has haunted both science and philosophy: nothingness. My research suggests a reframing of the void, not as the absence of everything, but as the potential for everything. The vacuum is not null, it is pregnant with possibilities. Quantum field theory supports this idea. Even empty space is teeming with activity. Virtual particles pop in and out of existence. Fields fluctuate. Energy is borrowed, repaid, and rearranged on scales so small we can only infer their presence. But I go further. I suggest that nothingness is not simply a backdrop to existence, it is a condition of emergence. In other words, nothingness is the raw substrate from which reality arises, not passively but through inherent instability. It is not zero, but a field of latent dimensions waiting to unfold. This has deep implications, not only for cosmology but for how we understand the arrow of time, the asymmetry of matter and antimatter, and the fine-tuning of physical laws. Perhaps what we call the Big Bang was not a beginning from nothing, but a transition within nothing, a phase shift from a timeless, dimensionless equilibrium into the structured, expanding reality we now inhabit. If this is true, then the origin of the universe is not an explosion, but a disturbance in stillness. From chaos to cosmos. In the wake of recombination, the universe entered its dark ages. No stars yet burned. Space was cold, silent, and slowly stretching. Hydrogen atoms drifted in darkness, pulled gently by the unseen hand of gravity. It would take hundreds of millions of years for the first lights to ignite. But even in this darkness, the seeds of structure were taking root. Tiny fluctuations, minute differences in density encoded in the cosmic microwave background, acted as blueprints for future galaxies. Regions just slightly denser than their surroundings began to attract more matter. Over time, these gravitational wells deepened, forming halos of dark matter and ordinary gas. Eventually, pressure and temperature reached a critical point. The hydrogen ignited. The first stars were born. These ancient stars, known as population 3 stars, were unlike anything we see today. Massive, short-lived, and made almost entirely of hydrogen and helium, they lived fast and died young. Their deaths, via titanic supernovae, seeded the cosmos with heavier elements: carbon, oxygen, nitrogen, and iron. From this cosmic alchemy came the building blocks of planets, life, and, eventually, consciousness. The light from these first stars began a slow transformation known as reionization, a process that ended the dark ages and made the universe transparent once again. Galaxies began to cluster, filaments and voids emerged, the universe blossomed into a web of complexity. From nothing, to light. From simplicity, to pattern. From dust, to mind. The fine-tuned universe. As galaxies formed and stars lit the void, another question surfaced, one that continues to puzzle scientists and philosophers alike: why does the universe seem so finely tuned for life and structure? If the expansion rate had been slightly faster, matter would never have clumped together. If it had been slower, the universe might have collapsed back into itself. The strength of gravity, the mass of the electron, the charge of the proton, all appear to be precisely balanced. Too much or too little, and stars couldn't form. Chemistry wouldn't work, life wouldn't be possible. Some propose this as mere coincidence. Others invoke the anthropic principle, the idea that we observe a universe suited for life because we exist to observe it. Still others suggest a multiverse, an infinite sea of universes, each with different laws, of which ours is just one where the conditions happen to be right. But whatever the answer, one thing is clear: the transition from primordial chaos to ordered cosmos is nothing short of miraculous. And perhaps, as I suggest, the miracle lies not in the emergence of something from nothing, but in the inherent capacity of nothingness to generate form, rhythm, and law. In this way, the origin of the universe is not merely a story of physical change, it is a testament to the creativity of the void, a cosmic act of becoming that continues to this day. Conclusion. The beginning that never truly ended. The story of the universe's origin is not just one of physics, it is a story of transformation, of emergence, of becoming. From a moment of unimaginable density and heat, space and time were born. From formless energy, matter congealed. From nothingness, everything. Yet this beginning was not a single event trapped in the past, it was a continuum, a perpetual unfolding. The universe is still expanding, still cooling, still creating. Stars are still born, galaxies still collide, and new worlds are forged in the crucibles of dying suns. And what of the nothingness from which it all came? My work invites us to rethink the void, not as an absence, but as a canvas of infinite potential. If nothingness is unstable, if it is inherently creative, then the universe is not an anomaly, it is an inevitability. A pulse in the quiet, a ripple in the eternal stillness. We are the children of that ripple, born from a universe that emerged not despite the void, but because of it. In understanding our beginning, we do not just look back, we look inward, outward, and forward. We are a way for the cosmos to know itself, a species just beginning to grasp the depth of its own story. And so, our journey continues. Chapter 2. The Architecture of the Cosmos. The universe is more than a vast expanse of stars and voids, it is an elegant structure woven with intricate patterns and governed by universal laws. From the quantum realm to the grandest galactic clusters, everything adheres to an architecture that is both complex and profoundly interconnected. Like a cathedral of unimaginable scale, the cosmos reveals its design not through blueprints, but through the subtle relationships among its components. Gravity binding stars to galaxies, forces shaping the orbits of planets, and dark matter sculpting the unseen skeleton of existence. The idea of a structured cosmos is not new. Ancient civilizations gazed at the heavens and saw order, constellations, planetary cycles, eclipses. These observations fed myths, calendars, and philosophies that mirrored the idea of a universe designed with purpose. Today, with our telescopes peering into the earliest moments after the Big Bang and simulations modeling the universe's growth, we continue that ancient quest to understand the cosmos, form and function. But now, we possess tools that allow us to quantify that architecture, and theories that hint at an even deeper, hidden order. Structure in the universe is not merely aesthetic. It determines the fate of stars, the formation of worlds, and perhaps the emergence of life itself. The architecture of the cosmos is, in many ways, the architecture of possibility. This chapter explores how the universe is built, from the majestic clusters of galaxies to the subatomic forces that govern matter itself. It is a journey into the scaffolding of reality. Let us begin by examining the most visible elements of the universe's architecture: galaxies, the vast, glowing cities of stars that populate the cosmos. Galaxies. The cities of the universe. Galaxies are the structural units of the universe, vast assemblies of stars, gas, dust, and dark matter held together by gravity. They range in size from dwarf galaxies with a few billion stars to giants containing hundreds of billions. Despite their diversity in scale and shape, galaxies all share a fundamental purpose. They are the birthplaces and homes of stars, planets, and potentially life. The Milky Way, our home galaxy, is a barred spiral galaxy stretching over 100,000 light-years in diameter. It contains an estimated 100 to 400 billion stars, including our Sun, orbiting a central bulge that harbors a supermassive black hole. Like other spiral galaxies, the Milky Way features graceful arms that spiral outward, dense with stellar nurseries and dust clouds. Other galaxies take different forms. Elliptical galaxies are more spheroidal in shape and typically contain older stars with little gas or dust, indicating a lack of recent star formation. Irregular galaxies, as their name suggests, lack any defined shape and are often the result of gravitational interactions or collisions with other galaxies. Galaxies are not isolated structures. They reside in groups, clusters, and even vast superclusters, bound together by gravity and shaped by their environments. Interactions between galaxies, through gravitational tugs, mergers, and collisions, are common across cosmic time. These events can trigger bursts of star formation, distort galactic shapes, and eventually lead to the formation of entirely new galactic structures. The formation of galaxies began in the early universe, a few hundred million years after the Big Bang. Tiny quantum fluctuations in the primordial plasma were amplified by gravity, creating regions of higher density. These regions attracted more matter, eventually collapsing to form the first protogalaxies. Over billions of years, these structures evolved, merging and growing into the galaxies we observe today. Galaxies are also key to understanding the large-scale distribution of matter in the universe. Their positions trace the underlying cosmic web, a vast network of filaments and voids that defines the architecture of the cosmos on the grandest scales. Studying galaxies gives us insights into the nature of dark matter, the history of star formation, and the fate of the universe itself. From their swirling spiral arms to the chaotic interactions that shape their evolution, galaxies are among the most fascinating and fundamental components of the universe. They are both the crucibles of creation and the monuments of cosmic history, each one a beacon in the vast night, carrying the story of the cosmos within its stars. The cosmic web, filaments, voids, and superclusters. Beyond individual galaxies lies a larger framework that defines the universe's grand design, the cosmic web. This web is the large-scale structure of the universe, a vast network of interconnected filaments, sheets, and voids that stretch across billions of light-years. It is within this intricate scaffolding that galaxies, clusters, and superclusters are distributed, bound together by gravity, guided by dark matter, and shaped by the universe's earliest moments. The idea of a cosmic web emerged from astronomical surveys and computer simulations that mapped the three-dimensional positions of galaxies. Instead of a random scatter, astronomers observed patterns, long threads of galaxies forming filaments, dense knots where filaments intersect forming clusters, and expansive empty regions called voids where few galaxies reside. These patterns are not merely aesthetic, they are the fingerprint of the universe's origin story. Cosmic filaments are the highways of matter, stretching tens to hundreds of millions of light-years in length. They are formed from the gravitational collapse of matter along the initial density fluctuations in the early universe. At the intersections of filaments lie galaxy clusters, regions of immense density and gravitational pull. Superclusters, among the largest known structures in the universe, are vast groupings of galaxy clusters connected by filaments, forming the backbone of the cosmic web. Voids, on the other hand, are the great empty spaces in the universe, sometimes spanning hundreds of millions of light-years. While seemingly devoid of matter, voids are essential to cosmic structure. Their low-density environments provide contrast to the filaments and clusters, and they play a role in the evolution of galaxies by influencing the flow of matter and the gravitational dynamics around them. One of the most detailed visualizations of the cosmic web comes from the Millennium Simulation, a massive computer model that tracks the evolution of billions of particles under the influence of gravity and dark matter. These simulations, along with deep space surveys like the Sloan Digital Sky Survey (SDSS), have confirmed that the cosmic web is a universal feature, stretching as far as we can observe. Understanding the cosmic web not only reveals the structure of the universe but also provides a framework for studying its composition, origin, and fate. It shows how matter is organized on the largest scales, how galaxies are influenced by their environment, and how the interplay between dark matter and gravity sculpts the cosmos. The web connects everything, from the most isolated galaxy in a void to the bustling heart of a supercluster. It is the skeleton of the universe, and we are strands woven within its cosmic tapestry. Dark matter and the invisible framework. While stars and galaxies shine brightly across the cosmic stage, the true scaffolding of the universe remains invisible. Dark matter, an elusive and enigmatic substance, composes the majority of matter in the universe, yet it does not emit, absorb, or reflect light. It interacts primarily through gravity, and it is this invisible framework that binds galaxies, shapes the cosmic web, and governs the dynamics of the cosmos on every scale. The evidence for dark matter first emerged in the 1930s when Swiss astronomer Fritz Zwicky observed that galaxies in clusters moved too quickly to be held together by the gravity of visible matter alone. Decades later, astronomer Vera Rubin's studies of galactic rotation curves confirmed that stars on the outskirts of galaxies were orbiting at speeds that defied expectations based solely on visible mass. These anomalies hinted at a hidden mass, dark matter, that envelops galaxies in vast, unseen halos. Today, dark matter is a central component of our cosmological models. It constitutes roughly 27% of the universe's total energy budget, far outweighing the 5% composed of ordinary, baryonic matter. Though we cannot see it directly, dark matter reveals itself through gravitational lensing, where its gravity bends the light of more distant objects, and through its influence on the formation and clustering of galaxies in the early universe. One of the most compelling pieces of evidence for dark matter comes from observations of galaxy collisions, particularly the Bullet Cluster. In this cosmic collision, the visible matter, hot gas emitting X-rays, was displaced from the gravitational center, which was traced using gravitational lensing. The separation of mass and visible matter strongly supports the existence of a dark, collisionless substance that does not interact electromagnetically. But what is dark matter? Despite its profound gravitational influence, its true nature remains a mystery. The leading candidates include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, hypothetical particles that interact only through gravity and possibly the weak nuclear force. Experiments like LUX, Xenon 1T, and the Large Hadron Collider continue the search for direct detection, while satellite missions like Planck and Euclid probe its cosmic influence. Dark matter is more than a cosmic curiosity, it is the foundation upon which galaxies and clusters are built. Without it, the universe would lack the structure we observe today. Understanding dark matter is essential not only for explaining how the universe looks but also for uncovering what it is made of and how it came to be. In the great architecture of the cosmos, dark matter is the unseen steel that holds the universe together. It shapes the growth of galaxies, the clustering of matter, and the very fate of the cosmos. Until we unveil its true nature, it will remain one of the deepest mysteries of existence, a ghostly architect in the shadows of the stars. Dark energy and the expanding universe. If dark matter is the invisible glue holding the universe together, then dark energy is the mysterious force pulling it apart. First discovered in the late 1990s, dark energy accounts for approximately 68% of the total energy content of the universe and is believed to be responsible for the accelerated expansion of space. The story begins with Edwin Hubble's discovery in the 1920s that galaxies are receding from us, implying that the universe is expanding. For decades, scientists assumed this expansion was slowing down due to gravity. However, observations of distant Type Ia supernovae in the 1990s revealed a surprising truth: the expansion of the universe is accelerating. This unexpected result suggested the existence of a repulsive force, dark energy, that counteracts gravity on cosmic scales. Unlike dark matter, which clumps and attracts, dark energy appears to be uniform and diffuse, exerting negative pressure that drives galaxies apart. The simplest explanation is Einstein's cosmological constant, lambda, a term he originally introduced and later dismissed, which represents a constant energy density filling space. In this model, dark energy is a property of space itself, growing in influence as the universe expands. Alternative theories propose that dark energy could be a dynamic field, known as quintessence, that evolves over time. Some even suggest modifications to general relativity to explain the observed acceleration without invoking a new energy component. Regardless of its nature, dark energy remains one of the greatest puzzles in modern cosmology. Its effects are profound. Dark energy not only accelerates expansion but also influences the fate of the universe. If its strength remains constant or increases, galaxies will drift farther apart, and the observable universe will become increasingly empty, a scenario known as the Big Freeze. If it varies dramatically, it could lead to more exotic outcomes like the Big Rip, where even atoms are torn apart by the expanding fabric of space. Measuring the properties of dark energy is a major focus of current and future missions, including the Dark Energy Survey, the Euclid spacecraft, and the Nancy Grace Roman Space Telescope. These efforts aim to map the universe's expansion history and refine our understanding of this elusive force. In the grand design of the cosmos, dark energy represents the dynamism of space itself, a silent architect of destiny. While we cannot see or touch it, its fingerprints are etched into the fabric of spacetime. To understand dark energy is to glimpse the forces shaping the future of everything we know. Chapter 3. The Fourth Dimension. The Nature of Time. Time has long been a subject of fascination and mystery. From the ancient philosophers to modern-day scientists, time has been studied, theorized, and pondered. Yet, despite our advances in understanding its effects, time remains one of the most elusive concepts in the universe. In our daily lives, time seems so ordinary, ticking away with each passing second, as clocks mark the rhythm of our existence. Yet, when we step back and look at time from a cosmic perspective, it becomes a profound and intricate force that shapes not only our lives but the very fabric of the universe. We are taught from an early age that time flows in one direction, from the past, through the present, and into the future. But this seemingly straightforward progression belies the complexity hidden beneath the surface. Time, as it turns out, is not just a measure of how long things take or how long we live. Time is a dimension, just like the three spatial dimensions we are familiar with. In fact, time is often referred to as the fourth dimension, a crucial component of the fabric of spacetime that governs the behavior of everything in the universe. Time in the context of space and spacetime. The idea of time as a dimension was revolutionized by Albert Einstein's theory of relativity. Prior to Einstein, time was understood in much the same way that everyday experience presents it, a constant, unchanging progression that flows steadily from the past into the future. However, Einstein's special and general theories of relativity radically altered our understanding of both space and time. In Einstein's view, space and time are not separate entities but are part of a unified whole known as spacetime. According to relativity, the presence of mass and energy warps the fabric of spacetime, much like how a heavy object placed on a rubber sheet causes it to bend. This warping of spacetime leads to what we experience as gravity, and it also influences the flow of time. A key consequence of this view of spacetime is time dilation, the idea that time does not pass at a constant rate everywhere in the universe. Time moves differently depending on your speed and the strength of gravitational fields you are in. For example, if you were to travel close to the speed of light, time would slow down for you relative to someone who remained stationary. Similarly, time runs slower near massive objects like black holes, where gravity is intense. This phenomenon has been confirmed in many experiments, such as those involving atomic clocks flown on airplanes or placed in different altitudes, where time is measured differently depending on the gravitational field. Einstein's concept of time as part of spacetime fundamentally changed how we think about the universe. Rather than seeing time as an absolute, linear progression, we now understand that time is flexible, relative, and influenced by the objects and forces in the universe. The arrow of time. One of the most intriguing aspects of time is its direction. We experience time as always moving forward, from past to present to future. This directional flow of time is often referred to as the arrow of time. But why does time seem to have this inherent direction, and why can't we move backward through it? The arrow of time is intricately linked to the concept of entropy, which is the measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can never decrease, it can only increase over time. This means that in any closed system, there is a natural tendency for things to become more disordered and chaotic as time progresses. This increasing entropy gives rise to the directionality of time. As systems evolve and entropy increases, time moves forward. The past, in a sense, is a state of lower entropy, while the future is one of higher entropy. The irreversible nature of this process gives time its arrow, preventing it from flowing backward. This phenomenon is often referred to as the thermodynamic arrow of time. Yet, the arrow of time is not limited to thermodynamics. It also manifests in the psychological arrow of time, the way we experience time as moving forward, from the memories of the past to the expectations of the future. Our conscious experience of time is inseparable from our perception of change, aging, and the unfolding of events. Time and causality, the fabric of reality. Time is not just a passive background for the unfolding of events, it is intricately connected with the concept of causality, which governs the relationship between cause and effect. The notion that every event has a cause and every cause leads to an effect underpins the very structure of our reality. But when we consider time in the context of relativity and quantum mechanics, the relationship between cause and effect becomes increasingly complex. In classical physics, the idea of causality is clear and linear. For every action, there is a corresponding reaction, and events unfold in a straightforward, predictable order. If you push a ball, it rolls; if you strike a match, it ignites. This direct cause and effect relationship mirrors our everyday experience of time. The past leads to the present, which leads to the future. However, relativity introduces a more nuanced view of causality. In a relativistic universe, events that occur at different locations in space and time may not be causally related in the same way they are in classical physics. The concept of the light cone is essential to understanding causality in relativity. It defines the region of spacetime that can influence or be influenced by a particular event. Events that lie within the light cone are causally connected, while those outside it are not, because they are separated by a distance that exceeds the speed of light, making communication or causal influence impossible. The light cone thus defines the limits of causality. It ensures that the laws of physics remain consistent and that information cannot travel faster than light. This concept also plays a critical role in the cosmic horizon, the furthest distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon, the universe is causally disconnected from us, meaning we cannot observe or influence events beyond this boundary. In quantum mechanics, the nature of causality becomes even more perplexing. In quantum systems, particles can exhibit behaviors that seem to defy causal reasoning. Quantum entanglement, for example, shows how two particles, once entangled, can instantaneously affect one another, no matter how far apart they are. This phenomenon, often referred to as spooky action at a distance, seems to challenge our classical understanding of causality and time. Some theories suggest that quantum mechanics may be pointing toward a deeper layer of reality, one where causality is not so easily defined and time behaves in fundamentally different ways. The nature of time, linear or cyclical. One of the oldest debates in philosophy and cosmology is whether time is linear or cyclical. In the Western scientific tradition, time has largely been conceived as linear. It moves in one direction, from the past, through the present, and into the future. This linear view of time is deeply embedded in our culture and understanding of history, as we see ourselves moving through time like a river flowing in one direction, unable to return to the past. However, many ancient cultures and philosophies, including Hinduism, Buddhism, and various indigenous traditions, have envisioned time as cyclical. In these systems, time is seen as a repeating cycle of creation, destruction, and rebirth. The universe undergoes periods of expansion and contraction, with each cycle eventually leading to a new beginning. This cyclical view is often associated with the concept of eternal recurrence, where the universe undergoes an infinite number of cycles, each one repeating the previous one in a seemingly endless loop. The cyclical view of time is also reflected in modern scientific models of the universe. For example, the Big Bang theory posits that the universe began from a singular point of immense density and temperature, expanding outward in what we perceive as the passage of time. But there are also theories that suggest the universe may undergo cycles of contraction and expansion, a concept known as the Big Bounce. According to this idea, the universe could have gone through a series of Big Bangs and Big Crunches, where it expands and contracts in a never-ending cycle. If true, this would imply that the flow of time is not linear but instead part of a repeating cosmic pattern. Some physicists have also proposed that time could have no intrinsic direction at all, a concept known as time symmetry. According to time symmetry, the laws of physics are equally valid whether time moves forward or backward. However, this symmetry is broken in macroscopic systems due to the increase in entropy, as described by the second law of thermodynamics. The arrow of time is the result of this increase in entropy, which forces time to move in one direction. Time and consciousness, the illusion of the present. The perception of time is not only influenced by the physical properties of the universe, but also by the way in which we experience and process it as conscious beings. Our minds construct a sense of continuous flow, moving from one moment to the next, from one, now, to another. But this experience of time as a continuous, present, is, in many ways, an illusion. Neuroscience has shown that our perception of the present moment is constructed by the brain. In reality, the information we process about the world around us is delayed by a few milliseconds. This delay means that we are always experiencing the past, albeit the past that occurred only a fraction of a second ago. In other words, the present we experience is not an instantaneous snapshot of reality but a constructed version of it, built by our brain as it integrates sensory input. This means that the experience of time is, at its core, subjective and mediated by our consciousness. Moreover, our perception of time can vary dramatically based on context. When we are focused on a task or deeply engaged in an activity, time seems to fly by. Conversely, when we are waiting for something or bored, time seems to drag. This subjective experience of time is also influenced by our age. As we grow older, time seems to pass more quickly, perhaps because as children we are constantly encountering new experiences and learning about the world, while as adults, we are more entrenched in routine and familiarity. In light of this, it's possible that the human experience of time, with its arrows, present moments, and memories of the past, might not be a universal truth but rather a construct of our consciousness. Some philosophers even suggest that time, as we perceive it, may be an illusion, a trick played on us by our minds. If time is indeed a construct of the mind, this raises profound questions about the nature of reality itself. Is the world as we experience it truly the way it is, or is it a mental model created by our brains? The role of time in the cosmos, cosmic time and the fate of the universe. Beyond the experience of time on Earth, the concept of time is crucial for understanding the universe as a whole. From the birth of stars to the death of galaxies, time is the canvas on which the story of the cosmos is written. The concept of cosmic time is essential for understanding the large-scale history of the universe, as it describes time in terms of the evolution of the universe from the Big Bang to its ultimate fate. Cosmic time begins with the Big Bang, around 13.8 billion years ago, and measures the age of the universe since that event. But cosmic time is not the same as the time experienced by observers in different locations of the universe. Because of the expansion of the universe and the effects of relativity, time flows differently in different regions. For instance, time near a massive object like a black hole passes more slowly than time in regions of weaker gravitational pull. Similarly, distant galaxies are receding from us due to the expansion of the universe, meaning the farther we look into space, the further back in time we are looking. The fate of the universe is deeply tied to time. The ultimate end of time, or the end of the universe itself, is a subject of intense speculation. There are a variety of hypotheses about how the universe might end, each involving different notions of time. The Big Freeze scenario posits that the universe will continue to expand forever, with galaxies drifting farther apart and stars burning out, eventually leading to a cold and lifeless universe. The Big Crunch, on the other hand, suggests that the universe's expansion will slow, halt, and reverse, leading to a collapse back into a singularity. Another possibility is the Big Rip, where the universe's expansion accelerates so rapidly that it tears apart galaxies, stars, and even atoms. Time in the future, time travel and the possibilities of the future. One of the most tantalizing ideas about time is the possibility of time travel, the ability to move backward or forward through time, much like we move through space. Time travel has long been a staple of science fiction, but it also raises serious scientific questions about the nature of time itself. The concept of time travel has fascinated thinkers for centuries, from the early philosophical musings of H.G. Wells' The Time Machine to more modern interpretations in films and literature. But can time travel actually be possible according to the laws of physics? The answer is more complicated than simply saying yes or no. In Einstein's theory of relativity, time travel into the future is theoretically possible. According to the principles of time dilation, time slows down for objects moving at speeds close to the speed of light. This means that if someone were able to travel at relativistic speeds, they would experience time at a much slower rate than someone who remained stationary. As a result, they could effectively travel into the future, since the passage of time for them would be slower compared to people on Earth. However, time travel to the past is much more problematic and remains a subject of intense debate. One of the key challenges is the so-called grandfather paradox, the logical dilemma that arises if someone were to travel back in time and change an event that would prevent their own existence, such as stopping their grandfather from meeting their grandmother. This creates a paradox, as it would mean the time traveler could never have existed in the first place to travel back in time. Some theoretical physicists have proposed that time travel to the past might be possible through wormholes, which are hypothetical tunnels in spacetime that could connect distant parts of the universe. If such wormholes exist and could be stabilized, they might provide a pathway for time travel. However, the idea of traversing through wormholes is still highly speculative, and there is no experimental evidence to support their existence. Another idea proposed by physicists is the concept of closed time light curves, CTCs, which are solutions to the equations of general relativity that allow for paths through spacetime that loop back on themselves. These curves could, in theory, allow for time travel to the past. However, the existence of CTCs remains purely theoretical, and there are unresolved questions about whether they could be physically realized. While time travel remains firmly in the realm of science fiction, it offers profound insights into the nature of time itself. The paradoxes and challenges posed by time travel highlight the deep, mysterious qualities of time and the limitations of our current understanding. The psychological perception of time. The human experience of time, as discussed earlier, is heavily influenced by our subjective perception. Our brains construct a continuous flow of time, but our perception of it can vary greatly depending on our circumstances. For example, time often seems to move slowly when we are bored or waiting for something, and conversely, it flies by when we are engaged in an enjoyable activity. This perception of time is deeply tied to our emotions and experiences, making it a personal and fluctuating phenomenon. From a psychological perspective, our sense of time is also shaped by our memories and expectations. The way we recall past events can make them feel like they happened more recently or longer ago than they actually did. Similarly, our expectations for the future can influence our experience of the present moment. If we are anxious about an upcoming event, time may feel like it's dragging, while anticipation for something exciting can make it seem to fly by. The concept of presentism, the idea that only the present moment exists and the past and future are merely mental constructs, also plays into our perception of time. In contrast, the eternalism viewpoint suggests that past, present, and future are equally real, and that time exists as a dimension much like space, with all points in time existing simultaneously. Although this philosophical debate remains unresolved, it underlines the subjective nature of time as experienced by conscious beings. Moreover, our relationship with time changes as we age. Children, who are constantly encountering new experiences, often perceive time as moving more slowly, while adults, who become more accustomed to routines, tend to feel that time moves faster. This phenomenon, often called the time paradox of aging, suggests that our perception of time is not simply a passive reflection of the passage of seconds but is also shaped by our experiences, memories, and the way our brains process the flow of time. Time in the cosmos, the big picture. As we zoom out from the personal experience of time to the grand scale of the cosmos, we encounter time on a completely different level. Time in the universe is marked by the birth and death of stars, the evolution of galaxies, and the expansion of the universe itself. Each of these processes unfolds over immense stretches of time, much longer than the human lifespan or even the history of human civilization. The Big Bang, the moment when the universe began, marks the beginning of time as we know it. According to the prevailing cosmological model, the universe began as a singular point of infinite density and temperature, which rapidly expanded in what is known as cosmic inflation. This event set the stage for the formation of matter, galaxies, stars, and everything else in the universe. Time on a cosmic scale is not uniform. The expansion of the universe means that time itself is not felt the same way everywhere. As we look out into the cosmos, we are also looking back in time. Light from distant stars and galaxies takes millions, even billions, of years to reach us, meaning that the farther we look into space, the further back in time we are observing. The cosmic microwave background radiation, which is the afterglow of the Big Bang, provides a snapshot of the early universe, just a few 100,000 years after the event. It offers a glimpse into the state of the universe when it was a hot, dense soup of particles before matter cooled and formed the first atoms. The future of time in the universe is equally fascinating. The fate of the cosmos is still a subject of scientific inquiry, with various theories about how time will end. Whether through a big freeze, a big crunch, or a big rip, the ultimate end of time in the universe is a possibility that continues to intrigue scientists and philosophers alike. The ongoing expansion of the universe, driven by dark energy, suggests that the cosmos will continue to grow colder and more distant, with galaxies moving away from one another at increasing speeds. The passage of time, as we understand it, is tied to the very structure of the universe itself. The laws of physics that govern the cosmos dictate how time flows, from the birth of stars and galaxies to their eventual demise. These processes unfold over timescales that stretch beyond human comprehension, but they are integral to the unfolding story of the universe. Conclusion. Time, the elusive fourth dimension, is a force that shapes the very structure of the universe. From the bending of spacetime around massive objects to the psychological experience of moments passing by, time permeates every aspect of existence. While we experience time as a constant, unidirectional flow, its true nature is far more complex. In the vast cosmos, time operates on scales far beyond human experience, from the rapid ticking of atomic clocks to the slow, steady march of cosmic evolution. Through the lenses of relativity, quantum mechanics, and cosmology, we have learned that time is not simply a linear progression, but a malleable and mysterious dimension of the universe. As we continue to explore the nature of time, from the mechanics of spacetime to the metaphysical implications of its flow, we come to realize that time is not merely a backdrop for the events of the universe. It is an active participant in shaping the cosmos, and its full understanding may one day unlock some of the deepest mysteries of existence itself. Chapter 4. The Life and Death of Stars. From the moment humans first gazed at the night sky, the stars have beckoned with silent wisdom, each one a distant sun blazing across the vast sea of time. To the ancients, they were gods and ancestors, to sailors, they were guides, and to us, they are luminous witnesses to the evolution of the universe. But stars, like all things, are mortal. Their lives span billions of years, yet they are born, they evolve, and they die. And in their death, they often seed the cosmos with the ingredients for life. This chapter is a journey into the life cycle of stars, how they form, burn, transform, and sometimes explode in magnificent finales. It's a story of nuclear alchemy, cosmic recycling, and the quiet drama of time on a stellar scale. The birth of a star. The story begins in darkness. Stars are born in vast, cold molecular clouds composed primarily of hydrogen and helium, speckled with dust and trace elements, remnants from earlier stars. These clouds drift silently through the galaxy, invisible to the naked eye but glowing in infrared. Under the pull of gravity, certain regions within the cloud begin to collapse. As they do, the cloud fragments and contracts, forming dense clumps, protostars. As matter falls inward, gravitational energy converts into heat. Deep within these cores, temperatures and pressures rise until a threshold is crossed. Nuclear fusion ignites. Hydrogen atoms begin fusing into helium, releasing immense energy. A star is born. The balance between gravity pulling inward and fusion pushing outward defines the new star's stability, a balance it will maintain for most of its life. Life on the main sequence. Once fusion stabilizes, the star enters the main sequence phase, where it will spend the majority of its life. The position of a star on this sequence, visible on the Hertzsprung-Russell (HR) diagram, depends primarily on its mass. A small red dwarf may burn for hundreds of billions of years, living slow and steady lives. Our Sun, a yellow G-type star, will last around 10 billion years total. Massive blue stars, burning through their fuel rapidly, may only live a few million years. The nuclear furnace in a star's core converts hydrogen to helium, generating light and heat that radiate outward. This radiation is the very light we see when we look up at the sky, photons that may have traveled for thousands of years before reaching us. Stars are not static. Over time, fusion byproducts build up. Helium accumulates in the core, and the balance begins to shift. Giant phases and core collapse. When a star exhausts its hydrogen, fusion halts in the core. Gravity resumes its work, compressing the star's heart, which grows hotter and denser. Hydrogen fusion begins in a shell around the core, and the outer layers expand. The star swells into a red giant. For low to intermediate mass stars like the Sun, the core eventually becomes hot enough to fuse helium into carbon and oxygen. But this cannot last. Once the helium is depleted, fusion ceases entirely in the core. The outer layers drift away, forming a planetary nebula, while the core cools into a white dwarf, a dense, Earth-sized remnant of stellar ash. Massive stars follow a more dramatic path. Their cores fuse heavier and heavier elements. Carbon into neon, neon into oxygen, oxygen into silicon, and silicon into iron. But iron fusion consumes energy, rather than releasing it. At that moment, the star's fate is sealed. Supernovae. Death is creation. When a massive star can no longer support itself, its iron core collapses under gravity's inexorable pull in a fraction of a second. Protons and electrons are squeezed into neutrons, and the outer layers rebound off this collapsing core in a cataclysmic explosion, a supernova. Supernovae are among the most energetic events in the universe, outshining entire galaxies for brief moments. The explosion hurls elements like carbon, oxygen, calcium, and iron into the cosmos, elements forged in the star's final moments or in the explosion itself. These explosions don't just end stars, they begin new stories. Their shockwaves compress nearby gas clouds, triggering new rounds of star formation. In this cosmic recycling, stars die so that others may live. If the remaining core is between about 1.4 and 3 solar masses, it becomes a neutron star, a city-sized object so dense that a teaspoon would weigh billions of tons. If it is more massive still, even neutrons collapse, and a black hole is born. Stellar remnants, white dwarfs, neutron stars, and black holes. The afterlives of stars are as varied as their lives. White dwarfs, the final state of low-mass stars. These slowly cool and fade over billions of years, eventually becoming hypothetical black dwarfs, though the universe is not old enough for any to yet exist. Neutron stars. These incredibly dense remnants often spin rapidly, emitting beams of radiation from their magnetic poles, pulsars. Their structure is exotic, possibly containing superfluid neutron matter or even quark matter. Black holes. The end state of the most massive stars, black holes bend space and time so severely that not even light can escape. They are invisible, yet their presence is inferred by their gravitational pull on nearby stars or the light they bend and consume. These remnants are the tombstones of stellar life, and yet, from them, galaxies evolve, light bends, and mysteries persist. We are stardust, the cosmic connection. Every atom of carbon in your body was forged in a star. The iron in your blood came from a supernova. The calcium in your bones, the oxygen you breathe, the silicon in your phone, all born in stars long dead. This isn't poetic metaphor, it's scientific truth. We are literally made of star stuff, as Carl Sagan famously said. The atoms that form you were scattered by dying stars billions of years ago, carried by gas clouds, reassembled in the sun, and later in the earth, and finally, in you. In this sense, we are not separate from the stars. We are their children. Stellar stories. The mythology and science of famous stars. Stars have always been characters in our myths. Betelgeuse, in Orion, a red supergiant nearing its death, has captured imaginations with its irregular dimming. Could it explode soon? Sirius, the dog star, is the brightest in our night sky, a binary system with a white dwarf companion. Proxima Centauri, the closest star to our Sun, hosts a planet in its habitable zone, a prime candidate for future exploration. Each star we name becomes a mirror, reflecting not only its light, but our longing for meaning in the cosmos. The tools of revelation. We know the lives of stars not from watching one star evolve, but from studying many stars at different stages. It's like learning human life by observing infants, teenagers, adults, and elders, not one individual, but many. Astronomers use HR diagrams to map a star's luminosity and temperature. Spectroscopy to determine chemical makeup. Parallax to calculate distance. Telescopes like Webb, Hubble, and Gaia to watch stars form, live, and die. With these tools, we have become readers of stellar history. The fate of the Sun. In 5 billion years, our Sun will die. It will become a red giant, perhaps swallowing Earth. Later, it will shed its layers and leave behind a white dwarf. Earth will either be incinerated or frozen, orbiting a ghost. This gives cosmic urgency to our dreams of space travel. If life is to continue, it must leave Earth, as children grow and leave home. Civilization around a dying star. Imagine a future civilization orbiting a red giant. Their sun swells, their oceans boil, and yet they build sky mirrors to reflect light. Subterranean cities, stories of cooler days. As the star dies, they launch arcs to other systems, seeking rebirth. Some remain behind, guardians of a fading world. It's fiction, or is it? Legacy of stars, beyond the physical. Stars don't just shape matter. They shape time. The death of stars drives the evolution of galaxies. Without stellar death, there would be no renewal, no complexity, no us. Each star is a book in the cosmic library. Each one adds a chapter to the universe's grand narrative. And every night, when we look up, we are reading it. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. Carl Sagan. Chapter 5. Black Holes and Beyond. Black holes have long been one of the most captivating and enigmatic entities in the cosmos. These immense objects are characterized by gravitational forces so powerful that they distort space-time itself. The pull from a black hole is so intense that nothing, not even light, can escape its grasp once it crosses a critical boundary known as the event horizon. While they may seem like cosmic vacuum cleaners that devour everything in their path, black holes are far from simple. They are among the most important objects in the universe for understanding space-time, the nature of matter, and even the structure of the cosmos itself. The idea of a black hole might sound like science fiction, but the theory behind them has been rooted in the laws of physics for over a century. The fundamental concepts that underpin black holes stem from Albert Einstein's theory of general relativity and earlier models. However, black holes only truly became a subject of serious scientific inquiry in the 20th century when scientists, armed with advanced tools and ideas, began observing and mathematically modeling their behavior. Today, black holes offer a laboratory for testing the limits of our understanding about the very fabric of reality itself. The birth of black holes. Black holes are typically formed from the remnants of massive stars that have reached the end of their life cycle. The process begins when a star, having exhausted its nuclear fuel, experiences a dramatic collapse. Stars undergo nuclear fusion in their cores, which creates outward pressure that counteracts the inward force of gravity. Once the nuclear fuel is depleted, the balance between these two forces is lost. The star's core begins to contract while its outer layers may expand. If the star's mass is sufficiently large, about 3 times the mass of our Sun, this contraction leads to the formation of a black hole. The collapse of the star is so intense that it results in an event horizon, the boundary beyond which no information or matter can escape. The collapsing core becomes a singularity, a point of infinite density where space-time becomes infinitely warped. The singularity lies at the center of the black hole, surrounded by the event horizon. This process of star collapse is known as stellar collapse, and it is a fascinating phenomenon because it demonstrates the clash between two of the most fundamental forces in nature, the strong nuclear force that holds atoms together and the gravitational force that pulls matter into the black hole. In the case of massive stars, gravity wins, pulling everything into the singularity. Singularities. The heart of the black hole. At the center of a black hole lies a mysterious and paradoxical object known as the singularity. The singularity is a point of infinite density where the curvature of space-time becomes infinite, and the laws of physics as we understand them no longer apply. In general relativity, a singularity represents a breakdown of the equations that describe gravity, suggesting that it is a place where our current theories fail to provide answers. The singularity is not something that can be directly observed. It is hidden within the event horizon, making it effectively inaccessible to any form of observation. What happens at the singularity? No one knows for sure, because no experiment or observation can reach it. At this point, gravitational forces become so strong that they overwhelm all other forces, including the electromagnetic force, which holds atoms and molecules together. The physics of singularities presents one of the most profound challenges in modern science. While general relativity provides a detailed description of the gravitational field around a black hole, it says very little about what happens at the singularity itself. The resolution of this problem is likely to come from a theory of quantum gravity, which seeks to combine the principles of quantum mechanics with general relativity. Quantum mechanics, which governs the behavior of particles at the smallest scales, offers a radically different view of the universe compared to general relativity. For example, in the quantum world, particles can exist in multiple states simultaneously, and their behavior is governed by probabilities. General relativity, on the other hand, is deterministic, meaning that it predicts the future behavior of objects based on their present state. Combining these two theories into a unified framework that can explain phenomena like singularities remains one of the key challenges of theoretical physics. The event horizon, a gateway to the unknown. Perhaps the most famous feature of a black hole is the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. It is the point of no return. Once an object crosses this boundary, it is inexorably drawn toward the singularity at the center of the black hole. The event horizon is not a physical surface but a region in space-time where the escape velocity exceeds the speed of light. The event horizon marks the limit where the gravitational forces of the black hole become so extreme that they prevent any information from escaping. This has led to the famous concept that black holes are black. They emit no light or radiation that can be detected from the outside. However, this does not mean that black holes are completely invisible. The region just outside the event horizon, known as the accretion disk, can be quite bright. As matter falls into a black hole, it heats up due to the tremendous friction and gravitational forces, emitting X-rays and other forms of radiation. The nature of the event horizon has also given rise to some mind-bending ideas in theoretical physics. According to general relativity, time slows down as an object approaches the event horizon. To an outside observer, the object seems to slow down and freeze at the event horizon, never quite crossing it. However, from the perspective of the object falling into the black hole, it would cross the event horizon without noticing anything unusual. This apparent paradox, the discrepancy between how time is perceived by an external observer versus the object itself, is one of the many mind-bending aspects of black hole physics. In addition, some theories suggest that the event horizon might not be as rigid as we once thought. In recent years, researchers have proposed that the event horizon could be fuzzy, rather than sharply defined. According to these ideas, the event horizon might behave more like a quantum foam, where space-time itself fluctuates at incredibly small scales. This idea is still very much in its infancy, but it suggests that the simple view of the event horizon as a clear-cut boundary might be more complicated than we initially imagined. Black holes and quantum mechanics, the search for a unified theory. One of the most exciting and challenging frontiers in modern physics is the search for a theory that unifies general relativity, which describes gravity, and quantum mechanics, which governs the behavior of particles at the smallest scales. While general relativity provides an excellent framework for understanding the behavior of large-scale cosmic objects like black holes, it is fundamentally incompatible with the principles of quantum mechanics, which deals with the behavior of subatomic particles. The problem is most acute near the singularity of a black hole. In this region, both the gravitational field is incredibly strong and the scales are so small that quantum effects should be significant. However, we currently lack a unified theory that can accurately describe what happens at these extreme conditions. Theoretical physicists have been working on a variety of approaches to reconcile general relativity and quantum mechanics. Among the most promising are string theory and loop quantum gravity, String theory posits that the fundamental building blocks of the universe are not particles, but rather one-dimensional strings that vibrate at different frequencies. These strings can manifest as different particles, depending on their vibrational modes. According to string theory, black holes may not contain a singularity at all, but instead may have a more complex internal structure composed of vibrating strings. This could resolve some of the paradoxes of black holes by providing a more complete picture of their interior. Loop quantum gravity, on the other hand, attempts to describe gravity as a quantum phenomenon by treating space-time itself as quantized. According to this theory, spacetime is made up of discrete units, rather than being a smooth continuum. In the context of black holes, this approach suggests that the singularity might be avoided entirely, as the quantization of spacetime would prevent the formation of an infinite density. While both string theory and loop quantum gravity are still speculative, they represent exciting new ways to approach the problem of reconciling the two great pillars of modern physics, general relativity and quantum mechanics. The role of black holes in the evolution of galaxies. Black holes are not isolated phenomena, they play a central role in the evolution of galaxies. In fact, there is growing evidence that black holes and galaxies are deeply intertwined, with each influencing the other in a cosmic feedback loop. Supermassive black holes, which are found at the centers of most large galaxies, are believed to be critical in the formation and growth of galaxies. One of the key ways black holes affect their galaxies is through accretion, the process by which gas and dust are pulled toward the black hole. As material falls toward the black hole, it forms an accretion disk, which can emit powerful radiation as the matter is heated up. This radiation can have significant effects on the surrounding galaxy, including regulating star formation. The intense radiation from the black hole can heat up nearby gas, preventing it from collapsing into new stars. This process is thought to help regulate the size and growth of galaxies. Moreover, black holes are believed to play a role in the merger and growth of galaxies. When two galaxies collide, their central black holes can also merge, forming a larger supermassive black hole. This process has been observed in simulations, and it is thought to be responsible for the formation of some of the largest black holes in the universe. The growth of these supermassive black holes is intimately tied to the evolution of their host galaxies. Observing black holes, the Event Horizon Telescope and New Frontiers. Despite their name, black holes are not invisible. While nothing can escape from inside the event horizon, the area around the black hole can be observed in various ways. The development of new astronomical instruments and techniques has allowed scientists to gather an incredible amount of data about these enigmatic objects. In 2019, the Event Horizon Telescope (EHT) captured the first-ever image of a black hole. This groundbreaking achievement revealed the shadow of the supermassive black hole at the center of the galaxy M87, located approximately 55 million light-years away from Earth. The image showed the dark center surrounded by a glowing ring of gas and dust that had been pulled toward the black hole's event horizon. This image was a momentous milestone in our understanding of black holes, providing direct visual evidence of their existence. The EHT is just one of many tools being used to study black holes. Future improvements to the EHT and the development of other observational technologies, such as gravitational wave detectors, will allow scientists to explore black holes in even greater detail. One of the most exciting possibilities is the observation of gravitational waves, ripples in spacetime caused by the acceleration of massive objects like black holes. In fact, the first detection of gravitational waves in 2015 came from the merger of two black holes, providing a new way to study these objects. The philosophical implications of black holes. While black holes are often discussed in terms of their physical properties, they also have profound philosophical implications. For centuries, scientists and philosophers alike have been captivated by the nature of time, space, and reality. Black holes, with their ability to stretch space-time and slow the passage of time, challenge many of our most basic assumptions about the universe. One of the most intriguing questions raised by black holes is the nature of information. According to classical physics, information that falls into a black hole is lost forever. However, this concept has been challenged by something called the black hole information paradox, which has sparked intense debate among physicists. The paradox arises from the conflict between quantum mechanics and general relativity. In quantum mechanics, information is never truly lost, even if it seems to be. If black holes were to destroy information, this would violate one of the most fundamental principles of quantum theory, known as the unitarity of quantum mechanics. Some have proposed that information is not destroyed in a black hole, but rather, it is encoded in subtle quantum states that exist just outside the event horizon. Others suggest that black holes may not be as absolute as we think, and that information might somehow be preserved through a process like holography. This principle suggests that all of the information within a volume of space can be encoded on its boundary, which could apply to black holes as well. In this view, everything that falls into a black hole may be preserved in a two-dimensional format at the event horizon, rather than being lost. The debate over the fate of information inside black holes remains unresolved, but it reflects the profound philosophical questions that arise when considering the limits of space-time. What happens to information when it is no longer accessible to the outside universe? Does the destruction of information imply a deeper flaw in our understanding of the universe itself? These questions force us to reconsider our understanding of reality, time, and the fundamental nature of existence. The future of black hole research. As we continue to advance our understanding of black holes, we also move closer to some of the most pressing questions in modern physics. The nature of space-time, the connection between gravity and quantum mechanics, and the structure of singularities all represent areas where new discoveries could lead to groundbreaking revelations about the universe. The future of black hole research is tightly connected to the future of technology and observation. New instruments, like the James Webb Space Telescope and advanced gravitational wave detectors, will offer more detailed insights into the behavior of black holes and the regions surrounding them. These observations will not only provide more data about the locations, sizes, and compositions of black holes but also offer new perspectives on how they interact with their environments. One of the most exciting developments in black hole research is the possibility of detecting black hole mergers through gravitational waves. When two black holes spiral toward each other and merge, they release a burst of gravitational waves, ripples in space-time that can be detected by sensitive instruments on Earth. These detections allow scientists to study the physics of black holes in real time and could lead to significant breakthroughs in our understanding of gravity and the nature of space-time. Moreover, the study of supermassive black holes, those lurking at the centers of most galaxies, will likely reveal more about the formation and evolution of galaxies themselves. There is growing evidence that supermassive black holes may play an active role in regulating galaxy growth and star formation. Understanding this relationship could unlock new insights into the development of the universe on the largest scales. As research into black holes advances, the potential for discovery is virtually limitless. The mysteries of these cosmic giants lie at the intersection of gravity, quantum mechanics, and the very structure of space and time. Black holes may hold the key to unlocking some of the deepest secrets of the universe, from the origins of cosmic structures to the ultimate fate of the universe itself. Conclusion. Black holes are among the most fascinating and perplexing objects in the universe. From their birth in the collapse of massive stars to their central role in the evolution of galaxies, they are essential to understanding the cosmos. The intense gravitational forces of black holes stretch space-time to its limits, offering a natural laboratory for studying the fundamental nature of matter, energy, and space itself. The research into black holes continues to advance at a rapid pace, with new observations shedding light on their behavior and their interactions with the surrounding universe. Yet, despite all our progress, black holes remain full of mysteries. Their singularities defy our current understanding of physics, and their event horizons challenge our concepts of time and information. As our technology improves, and our theoretical models evolve, we will undoubtedly continue to explore the fascinating and enigmatic nature of black holes, pushing the boundaries of our understanding about space, time, and the fundamental forces that shape the universe. Ultimately, black holes offer more than just an opportunity to study extreme gravitational forces. They hold the potential to reveal the deepest secrets of the cosmos, from the origins of space and time to the nature of reality itself. Through the continued study of black holes, we may uncover answers to some of the most profound questions in science and philosophy, questions about the nature of existence, the fabric of the universe, and the limits of human knowledge. Chapter 6. Gravity and the Fabric of Spacetime. Gravity is the quiet architect of the cosmos, a force so subtle we barely notice its presence, yet so powerful it shapes the destiny of stars, galaxies, and even the universe itself. It governs the tides, anchors the moon in orbit, binds solar systems, sculpts the structure of galaxies, and dictates the large-scale dynamics of the cosmos. For millennia, it was a mystery, felt but not understood. Then came revolutions in thought that revealed gravity not as a force pulling at a distance, but as the very curvature of spacetime. This chapter dives deep into gravity, tracing its conceptual evolution from Newton's apple to Einstein's spacetime, to black holes and gravitational waves. We'll explore how gravity is not just a force, but a manifestation of geometry, a dynamic dialogue between matter and the fabric of reality itself. The classical view, Newton's law of Universal gravitation. In the late 17th century, Isaac Newton provided the first mathematical description of gravity. With his law of universal gravitation, Newton proposed that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. F equals g times m r squared. This elegant formula unified celestial and terrestrial mechanics. The same force that made apples fall also held the moon in orbit. Newton's theory, embedded within the larger framework of classical mechanics, accurately described planetary motion, projectile trajectories, and more. However, Newton's theory had its limits. It assumed gravity acted instantaneously at a distance, a notion that conflicted with later developments in electromagnetism and the finite speed of light. Moreover, it could not account for anomalies like the precession of Mercury's orbit. These discrepancies hinted at a deeper truth. Einstein's revolution. Gravity is geometry. Albert Einstein transformed our understanding of gravity with his general theory of relativity in 1915. Gravity, he proposed, is not a force transmitted through space. Instead, it is a curvature of spacetime caused by the presence of mass and energy. Imagine space and time as a flexible sheet. When a massive object like a star or planet sits on this sheet, it creates a depression. Other objects moving nearby are drawn toward this dent, not because they are being pulled, but because they are following the natural curves of the warped spacetime. Einstein encapsulated this with his field equations. R half a gram r plus lambda g equals 8 pi g c to the power of 4t. On the left side, the geometry of spacetime. On the right, the matter and energy content. Matter tells spacetime how to curve. Curved spacetime tells matter how to move. This profound insight didn't just replace Newton's theory, it redefined the very arena of physics. No longer a static backdrop, spacetime became dynamic, elastic, and responsive. The equivalence principle. Falling into insight. At the heart of general relativity lies the equivalence principle. Einstein realized that being in freefall due to gravity is locally indistinguishable from floating in space. This principle formed the philosophical foundation of general relativity. Think of an astronaut in orbit. She feels weightless not because there's no gravity, but because she's in constant freefall around Earth. She's following a curved path, called a geodesic, through spacetime. Geodesics are the natural trajectories in curved space, much like great circles on a globe represent the shortest distance between 2 points. This idea radically shifted the way we think about motion. In Newtonian physics, forces cause acceleration. In Einstein's view, gravity is not a force, it's the natural motion through curved spacetime. Time and gravity, the warping of clocks. Einstein's theory revealed that time, like space, is affected by gravity. Clocks in strong gravitational fields tick more slowly than those in weaker ones. This phenomenon, called gravitational time dilation, has been confirmed by countless experiments. For instance, atomic clocks flown on high-altitude airplanes or placed on mountaintops run faster than identical clocks at sea level. GPS satellites must account for both special relativity due to their high speed and general relativity due to their altitude to provide accurate positioning. This warping of time means that in a strong gravitational field, like near a black hole, time effectively slows down. The deeper one falls into a gravitational well, the more time stretches. In extreme cases, it almost comes to a halt from an outside observer's point of view. Black holes. Gravity run wild. Few phenomena showcase the extremity of gravity like black holes. These are regions where spacetime curvature becomes so intense that nothing, not even light, can escape. According to general relativity, when a massive star collapses under its own gravity at the end of its life, it can form a singularity, a point of infinite density and zero volume. Surrounding this singularity is the event horizon, the boundary beyond which escape is impossible. Once inside, all paths lead inevitably inward. Time and space switch roles. The singularity is not just a point in space, it is a moment in time you cannot avoid. Black holes are no longer just theoretical. We've observed their gravitational effects on stars, detected the X-rays emitted from their accretion disks, and even captured the first image of a black hole's shadow in 2019. And yet, black holes challenge our understanding. At the singularity, Einstein's equations break down. We need a theory of quantum gravity to explain what lies within. Gravitational waves. Echoes in the fabric. In 2015, a century after Einstein's prediction, we detected gravitational waves, tiny ripples in spacetime produced by cataclysmic events like merging black holes. These waves stretch and squeeze space itself as they pass through Earth, altering distances by less than the width of a proton. The Laser Interferometer Gravitational Wave Observatory (LIGO) made this historic detection, confirming another key prediction of general relativity. Since then, dozens more have been recorded. Gravitational wave astronomy is now an emerging field, giving us a new way to observe the universe. Unlike light, which can be blocked or absorbed, gravitational waves pass through matter unimpeded. They offer a pristine view into the most violent events in the cosmos. Cosmology and the shape of the universe. General relativity laid the groundwork for modern cosmology. The theory predicts that the universe should be either expanding or contracting. Observations by Edwin Hubble in the 1920s confirmed the expansion, leading to the development of the Big Bang model. The curvature of spacetime also helps define the geometry of the universe. If the universe has enough mass energy, it is closed, spherical. If it has too little, it is open, hyperbolic. Just the right amount yields a flat universe. Measurements of the cosmic microwave background radiation, especially from the Planck satellite, suggest that the universe is flat, on the largest observable scales, with small fluctuations indicating the seeds of galaxies. However, gravity alone does not explain everything. The accelerated expansion of the universe, discovered in the 1990s, suggests the presence of dark energy, a mysterious repulsive component of spacetime. Its nature remains one of the deepest puzzles in physics. Gravity versus quantum mechanics. Despite its success, general relativity doesn't play well with quantum mechanics, the theory governing the subatomic world. In the quantum realm, forces are mediated by particles, the electromagnetic force by photons, the strong force by gluons, and so on. Gravity is assumed to be mediated by the hypothetical graviton, but no such particle has been found. Attempts to unify gravity with quantum mechanics have led to theories like string theory, which posits that particles are one-dimensional strings vibrating in higher-dimensional space. Loop quantum gravity, which quantizes spacetime itself into discrete chunks. Causal set theory, which imagines spacetime as a growing network of discrete events. These theories are mathematically elegant, but none has been conclusively verified. The challenge lies in the weakness of gravity. It's vastly weaker than other forces, making it hard to test in a laboratory. Only in the most extreme environments, like near black holes or the Big Bang, do both quantum and gravitational effects matter equally. Manipulating gravity. Science fiction or future science. Throughout history, humanity has dreamed of mastering gravity. From levitation in ancient myths to artificial gravity in science fiction, controlling gravity has fascinated minds for centuries. So far, we've only learned to resist it, through muscle, machines, and rockets. But could we ever engineer gravity? Some speculative ideas include warp drives, which manipulate spacetime to travel faster than light. Gravitational shielding, a hypothetical concept to block or reduce gravity. Mass manipulation, using exotic matter to bend spacetime on demand. While such ideas remain in the realm of speculation, research in advanced propulsion, general relativity, and quantum field theory might one day turn science fiction into science fact. The human experience in a gravitational universe. Gravity affects not just stars and galaxies, it shapes human existence. It pulls us to the Earth, gives us weight, and subtly governs our physiology. Long-term exposure to microgravity in space causes muscle atrophy, bone loss, and fluid redistribution. Understanding gravity is essential for future space exploration. Mars missions, lunar bases, and deep space travel all depend on mitigating the effects of reduced gravity or designing habitats with artificial gravity. Moreover, gravity influences our perception of time, space, and even reality. When we gaze at the stars, we're looking back in time, seeing ancient light warped by gravitational lenses and stretched by cosmic expansion. Closing reflections. In curved space, we find meaning. Gravity is more than a force, it is the silent weaver of existence. It whispers the shape of the universe, guides the dance of galaxies, and sculpts the passage of time itself. Through Newton, we learned its rules. Through Einstein, we glimpsed its depth. Through black holes, waves, and expanding space, we continue to uncover its mysteries. As I reflect on gravity, I'm reminded of how something so omnipresent can still be so enigmatic. It humbles us, yet invites us to soar. It binds us to the Earth, yet calls us to the stars. In every fall, every orbit, every wave, gravity speaks the geometry of the universe. And in that geometry, we find not just physics, but purpose. Chapter 7. Parallel Realities in the Expanding Universe. In this chapter, we explore two of the most profound and perplexing concepts in modern physics, the expanding universe and parallel realities. Both ideas challenge our traditional understanding of space, time, and existence. While the expanding universe offers insight into the vast dynamics of cosmic growth, parallel realities, suggested by quantum mechanics and cosmology, invite us to question the very nature of reality itself. By examining these concepts in detail, we can begin to understand the deeper mysteries of the cosmos. The expanding universe. In the early 20th century, the prevailing view of the universe was that it was static, neither growing nor shrinking, but eternal and unchanging. This view was shattered by Edwin Hubble's observations in the 1920s, which revealed that distant galaxies were moving away from us. The greater the distance, the faster they seemed to be receding. This observation provided the first concrete evidence that the universe was expanding. Hubble's law, named after him, describes the linear relationship between the distance of a galaxy and its recessional velocity, cementing the idea that the universe was not only dynamic but constantly changing. The expanding universe concept leads to one of the most important ideas in cosmology, the Big Bang theory. The idea is that if galaxies are moving away from each other, then, at some point in the past, they must have been closer together. Tracing this expansion backward, we arrive at a singularity, an infinitely dense and hot point where the laws of physics as we know them no longer apply. This singularity represents the origin of both time and space, approximately 13.8 billion years ago. From this moment, the universe began to rapidly expand, cooling down as it spread out, eventually giving rise to galaxies, stars, and other cosmic structures. However, the expansion of the universe did not stop after the Big Bang. In the late 1990s, astronomers made another groundbreaking discovery. The rate of the universe's expansion was accelerating, not slowing down. This discovery was attributed to a mysterious force called dark energy. Dark energy, which makes up about 68% of the universe's total energy content, acts in opposition to gravity, driving the acceleration of the universe's expansion. This force remains one of the most perplexing and least understood components of our cosmos. The accelerating universe and its ultimate fate. With the acceleration of the expansion, the fate of the universe becomes even more uncertain. There are three primary scenarios for the long-term future of the universe, depending on the interplay between dark energy, gravity, and the shape of space-time. 1. The Big Rip. If dark energy continues to increase its influence, the expansion of the universe could accelerate to the point where galaxies, stars, and even atoms are torn apart. This scenario, known as the Big Rip, would result in the ultimate destruction of everything in the universe. 2. The Big Crunch. If gravity eventually overcomes the effect of dark energy, the universe could begin to contract. In this scenario, galaxies, stars, and planets would collapse inward, eventually ending in a massive implosion, known as the Big Crunch, returning the universe to a hot, dense state. 3. The Big Freeze. If the rate of expansion continues at a more gradual pace, the universe could experience a big freeze. In this scenario, galaxies would drift further apart, stars would burn out, and the cosmos would become increasingly cold and dark. This outcome suggests a slow decline, with no violent end but a gradual fade into emptiness. Understanding the fate of the universe is one of the most profound challenges in cosmology. The next few decades may bring new discoveries, perhaps leading to a greater understanding of the role of dark energy or even new forces that govern the cosmos. For now, we can only theorize based on our observations of the present and extrapolate to the future. The multiverse. The nature of parallel realities. While the expanding universe tells us about the large-scale dynamics of space, the idea of parallel realities, sometimes referred to as the multiverse, deals with the fundamental nature of reality itself. The multiverse theory posits that there could be multiple, perhaps infinite, universes coexisting alongside our own. These universes could be entirely different from ours, with different physical laws, constants, and histories. The concept of parallel universes challenges everything we know about our place in the cosmos and the limits of human understanding. There are several variations of the multiverse hypothesis, each rooted in different branches of modern physics. The notion that multiple universes exist is not just a philosophical idea but a legitimate scientific proposition, supported by mathematical frameworks and theoretical models. The quantum multiverse. The many worlds interpretation. One of the most famous theories that suggests the existence of parallel universes is the many worlds interpretation (MWI) of quantum mechanics. Quantum mechanics, the branch of physics that deals with particles on the smallest scales, has produced many counterintuitive and baffling results. One of the most perplexing aspects of quantum theory is the concept of superposition. Particles, such as electrons, exist in a state of multiple possibilities until they are measured. Once observed, the particle collapses into one of those possibilities. The many worlds interpretation, proposed by physicist Hugh Everett in 1957, suggests that instead of collapsing into one state, the universe splits into multiple branches. Each time a quantum event occurs, all possible outcomes happen simultaneously in separate, parallel universes. For instance, in one universe, you might have chosen to stay in bed this morning, while in another universe, you woke up early and went for a run. Every choice, every event, creates new parallel realities. In this way, the many worlds interpretation offers an elegant solution to the paradox of wavefunction collapse. Instead of requiring the universe to collapse into a single reality, the many worlds theory suggests that all possibilities are realized, but in separate worlds. This means that there could be an infinite number of versions of ourselves, each living in a universe where different decisions were made. While the many worlds interpretation offers a fascinating way to think about the nature of reality, it also raises difficult philosophical questions. If every possible outcome occurs in some universe, what does this mean for concepts like free will or fate? Are we truly in control of our actions, or are we merely following the inevitable path that exists in an infinite set of realities? The cosmic multiverse, inflation and pocket universes. Parallel realities don't just exist at the quantum level, they may also arise on the cosmic scale. The theory of cosmic inflation, proposed by Alan Guth in the 1980s, suggests that the universe underwent a period of rapid expansion during the first moments after the Big Bang. This inflationary phase helped to explain the large-scale homogeneity of the universe, as well as its observed flatness. However, inflation also predicts the existence of pocket universes, or bubbles, each with its own distinct properties. According to the theory, during inflation, different regions of space could have inflated at different rates, creating separate bubble universes. Each bubble could have different physical laws and constants, leading to a vast multiverse. In some of these universes, life could exist under very different conditions, while in others, the laws of physics may not allow for the formation of stable structures like atoms and stars. The existence of these pocket universes would provide a natural explanation for the fine-tuning of the constants in our own universe. If there are infinitely many universes, some of them would naturally have the right conditions for life to emerge, simply by chance. The string theory multiverse, the landscape of possibilities. String theory, which attempts to unify the forces of nature by describing particles as one-dimensional, strings, also suggests the existence of a multiverse. In string theory, the universe is not made up of point-like particles, but of tiny, vibrating strings. These strings can vibrate at different frequencies, and the configuration of their vibrations determines the properties of particles. String theory also predicts the existence of multiple extra dimensions, beyond the familiar three of space and one of time. In this framework, there is a vast landscape of possible universes. The extra dimensions could be curled up in different ways, leading to a variety of possible physical laws. Some of these universes would be very similar to ours, while others could have completely different laws of physics. According to some estimates, there could be up to 10⁵500 possible universes, each with different properties. The theory of a string landscape offers a tantalizing explanation for the fine-tuning of our universe. Perhaps our universe is just one of many, and we happen to live in one that is conducive to the emergence of life. The implications of parallel realities. The idea of parallel realities has profound implications for our understanding of the cosmos and our place within it. If multiple universes exist, it suggests that the cosmos is far more complex than we ever imagined. The existence of parallel worlds challenges our assumptions about the uniqueness of our universe and raises questions about the nature of existence itself. Are we just one tiny part of an infinite multiverse? Could there be versions of ourselves in other universes, living out different lives? Are our choices truly our own, or are they part of a greater cosmic web of possibilities? Moreover, the multiverse theory raises deep philosophical and metaphysical questions. If every possible outcome exists in some parallel reality, does this imply that every decision we make creates a new universe? How do we reconcile the existence of multiple realities with the concept of free will? And what does it mean for our understanding of life, death, and consciousness? These questions may never be fully answered, but they continue to inspire wonder and curiosity in scientists and philosophers alike. As we delve deeper into the mysteries of space, time, and the multiverse, we may uncover new insights that challenge the very fabric of reality. Conclusion. The expanding universe and the concept of parallel realities represent two of the most profound and transformative ideas in modern science. The expansion of the universe reveals a cosmos that is dynamic and ever-changing, while the multiverse theory opens the door to an infinite number of realities, each with its own set of possibilities. Both concepts push the boundaries of our understanding and invite us to think more deeply about our place in the cosmos. As we continue to explore the universe, these ideas will undoubtedly shape the future of cosmology and inspire new avenues of discovery and exploration. Chapter 8. Life in the Cosmos. Are we alone? It's a question that has echoed through the chambers of human thought for millennia, a question that ties mythology to science, poetry to physics. From the cave drawings of early humans to the golden records launched aboard the Voyager spacecraft, we have long pondered the possibility of other beings gazing skyward, wondering the same thing. This chapter explores that question in depth, through chemistry and astrobiology, equations and enigmas, telescopes and thought experiments, as we traverse the cosmic wilderness in search of companionship. The universal chemistry of life. When we think of life, we often picture lush earthly environments, coral reefs teeming with fish, rainforests echoing with birdsong, or the microscopic bustle of bacteria in a drop of pond water. But strip life down to its scaffolding, and what remains are atoms, mostly carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements form the basis of life on Earth. Remarkably, these same elements are common across the universe. Carbon chains have been detected in interstellar clouds. Water exists in molecular form in cold regions of space. Amino acids, the building blocks of proteins, have been found on meteorites. This universality suggests that life, or something like it, need not be an earthly anomaly. It may be an inevitable expression of chemistry under the right conditions. Carbon's versatility. Carbon deserves special attention. With its 4 bonding sites, carbon can form an incredible variety of molecular structures, from simple chains to complex ring systems. This versatility makes it uniquely suited for the complex chemistry of life. While some researchers have hypothesized silicon-based life in alternative environments, carbon remains the most likely candidate for any life we might discover. Water, the cosmic solvent. Water, too, appears to be abundant. It's been detected in the atmospheres of exoplanets, in the plumes of Saturn's moon Enceladus, and in the vast subsurface ocean beneath Europa's icy shell. Water is not only a solvent, it's a medium where molecules can move, react, and replicate. Its unique properties, such as a high heat capacity and ability to dissolve a wide range of substances, make it essential for life as we know it. The numbers game, the Drake equation. In an effort to quantify the uncertainty around extraterrestrial life, Dr. Frank Drake proposed a framework, now iconic in the field of SETI search for extraterrestrial intelligence. The Drake equation is not a formula for proof, but a tool for perspective. It asks us to consider each step that leads from stardust to speech. Let's break it down. N equals R times Fp times Na times Fl times Phi times Fc times L asterisk R asterisk, the rate of star formation in the galaxy approximately 1.53 stars per year. Fp, the fraction of those stars that have planetary systems. Na, the number of planets per system with environments suitable for life. Fl, the fraction of those planets where life actually appears. Phi, the fraction of life-bearing planets where intelligent life evolves. Fc, the fraction of intelligent civilizations that develop detectable technologies. L, the expected lifetime of such civilizations. Even conservative estimates suggest there could be dozens, even hundreds, of civilizations in the Milky Way alone. But the silence persists, leading to the paradox at the heart of our search. The Great Silence, Fermi's haunting question. In 1950, during a casual lunch conversation at Los Alamos, the physicist Enrico Fermi posed a deceptively simple question: where is everybody? Given the age of the universe, the number of stars, and the high probability of Earth-like planets, Fermi reasoned that intelligent civilizations should have emerged long before us, and some should have even colonized the galaxy by now. This contradiction, between the high probability of extraterrestrial civilizations and the complete lack of evidence, is known as the Fermi paradox. Proposed solutions. Filled circle the rare Earth hypothesis. Some scientists argue that while microbial life may be common, the evolution of complex, intelligent life may be extraordinarily rare. Factors such as a large moon to stabilize planetary tilt, plate tectonics, magnetic fields, and just the right level of atmospheric oxygen might be uncommon. Filled circle the great filter. Perhaps there is a bottleneck, a critical step in evolution that is extremely unlikely. This could lie behind us, suggesting we are rare survivors, or ahead of us, suggesting most civilizations self-destruct before reaching interstellar capability. The latter scenario carries an ominous warning about our future. Filled circle, they're hiding. Zoo hypothesis: maybe advanced civilizations choose not to contact us, either to allow our natural development, or because they consider us primitive and uninteresting. Like a cosmic wildlife preserve, Earth may be under quarantine. Filled circle communication limits. Civilizations may not use radio signals as we know them, or their communications may be too brief, narrow, or advanced for us to detect. Even on Earth, we're moving away from high-powered radio broadcasts in favor of tight-beam digital signals and fiber optics, rendering us nearly invisible to distant observers. Filled circle, we're early. It's also possible that intelligent life is only just beginning to blossom in the galaxy. Perhaps the universe is in its cosmic spring, and we're among the first to awaken. This silence, pregnant with potential meaning, continues to push both science and imagination. And while we listen to the stars, we look inward, studying Earth's most extreme environments for clues. Lessons from extremophiles. Life on Earth is astonishingly resilient. It thrives where logic once said it couldn't. Boiling sulfur springs, acidic lakes, deep-sea hydrothermal vents, and even radioactive waste. These extremophiles stretch the definition of habitability. Filled circle thermophiles and hyperthermophiles. These organisms love heat. Some flourish in environments above 100 degrees Celsius, near volcanic vents on the ocean floor. Their existence suggests that similar vents beneath icy moons could also harbor life. Filled circle halophils. These salt-loving microbes dwell in places like the Dead Sea or salt flats. They offer insight into how life might survive on Mars, where salt deposits and briny water have been detected. Filled circle acidophiles and alkaliphiles. Capable of surviving at extreme pH levels, these organisms thrive in battery acid-like environments or alkaline lakes, hinting that similar niches may exist on alien worlds. Filled circle radiodolorant life. The bacterium Deinococcus radiodurans can survive extreme radiation and desiccation. This trait could be useful in understanding how life might survive cosmic rays on unshielded planets or during interplanetary travel. Filled circle cryophiles. These cold-loving organisms survive in glacial ice and frozen tundra. Some remain dormant for thousands of years and reawaken when thawed, reminding us that even frozen moons may not be dead. What extremophiles teach us is profound. Life is not fragile, it is adaptable. Its range may be broader than we ever imagined. Mars, moons, and missions, the hunt for signs. Let us now turn our gaze outward, to the places in our own solar system that are prime candidates for alien life. The more we explore, the more we find that Earth is not alone in its potential for biology. Mars, the red enigma. Mars has always been tantalizing. Once imagined as a world of canals and civilizations, it's now a colder, quieter planet. But it is not lifeless in the geochemical sense. Evidence of water. NASA's rovers have confirmed that liquid water once flowed on the Martian surface. Today, there are seasonal streaks on slopes, recurring slope lini, that may indicate briny water activity. Organic molecules. The Curiosity rover detected organic molecules in ancient lakebed sediments, not life, but the ingredients of life. Methane mystery. Methane has been detected in varying amounts in the Martian atmosphere. On Earth, methane is often biological in origin. Could subsurface microbes be producing it? Missions like Mars Sample Return, ExoMars, and potential crewed expeditions in the 2030s aim to answer this question definitively. Europa and Enceladus. Oceans beneath ice. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are among the most exciting places in the search for life. Beneath their icy crusts lie global oceans, kept liquid by tidal flexing and possibly warmed by hydrothermal activity. Europa shows chaotic ice terrain that hints at subsurface movement, and its surface is rich in salts. Enceladus has geysers, literal plumes of water vapor erupting from its south pole, containing water, organic compounds, and silica particles. Future missions like Europa Clipper, NASA, and JUICE ESA will investigate these moons with cutting-edge instruments, seeking biosignatures in the ice and vapor. Titan, a different kind of chemistry. Saturn's largest moon, Titan, is a bizarre and beautiful world. Its rivers and lakes are made of methane and ethane. Its thick atmosphere is rich in organic compounds. Though it is incredibly cold, scientists speculate that life based on entirely different chemistry might be possible here, not water-based, but hydrocarbon-based. NASA's Dragonfly rotorcraft mission, set to launch in the 2030s, will explore Titan's surface, searching not only for prebiotic chemistry but for signs of life that may defy earthly definitions. Philosophical reflections. What it means if we are not alone. To search for life in the cosmos is not merely a scientific endeavor, it is a deeply philosophical one. The implications of discovering extraterrestrial life, especially intelligent life, would be profound and far-reaching. A new Copernican shift. Just as Copernicus displaced Earth from the center of the universe, discovering life elsewhere would displace humanity from its presumed biological uniqueness. We would no longer be the sole instance of nature's capacity for awareness, just one thread in a vast cosmic tapestry of consciousness. This would challenge long-held beliefs in religion, philosophy, and anthropology. Are we special? Are our moral codes universal? Or are they merely adaptations of one planetary species? Unity and humility. Paradoxically, discovering others might bring humans closer together. The idea that we are not alone could reduce nationalistic divisions and foster a planetary identity. Carl Sagan envisioned such unity, writing, "The Earth is a very small stage in a vast cosmic arena." But this realization could also humble us. Faced with civilizations possibly millions of years ahead, our pride might shrink, or evolve into awe and aspiration. Theological questions. Many religious traditions focus on humanity as central to creation. The existence of alien life would raise deep theological questions. Did God create life elsewhere too? Do other beings have souls, revelations, or spiritual systems? How would human religions adapt? Some faiths may interpret extraterrestrial life as part of a divine plan, others may resist the implications. Theologians and philosophers have already begun preparing for these scenarios, creating frameworks for interstellar ethics, spiritual inclusivity, and metaphysical pluralism. The future of the search. The next century promises a revolution in our quest for life. Next-generation telescopes. James Webb Space Telescope (JWST) and upcoming Nancy Grace Roman Telescope are capable of analyzing the atmospheres of exoplanets, searching for biosignatures like oxygen, methane, ozone, or combinations that suggest biological activity. Ground-based behemoths like the Extremely Large Telescope (ELT) and 30-meter telescope (TMT) will provide unprecedented resolution and spectroscopy for characterizing distant worlds. Biosignatures and technosignatures. While biosignatures focus on natural signs of life like gases or pigments, technosignatures look for signs of technology, such as laser pulses, industrial pollutants, or artificial satellites. These could indicate not just life, but intelligent life. SETI, search for extraterrestrial intelligence, continues to scan the skies for deliberate signals. Meanwhile, newer initiatives like Breakthrough Listen and LOFAR expand the hunt with eye-enhanced algorithms and wider frequency ranges. Interstellar missions. Projects like Breakthrough Starshot aim to send tiny spacecraft to nearby stars like Proxima Centauri, propelled by powerful lasers and traveling at a significant fraction of the speed of light. These probes, equipped with cameras and sensors, could one day return data from other planetary systems. Though still theoretical, such missions could allow humanity's first direct encounters with alien worlds. Speculative futures. Contact scenarios. If we do discover life, microbial or intelligent, how might it unfold? Scenario 1. Microbial life in our backyard. A robotic mission discovers microbial fossils on Mars, or living microbes in Enceladus' ocean plumes. This would confirm a second genesis in our solar system, proving that life is a cosmic inevitability. The public celebrates, funding for space science skyrockets. Earth's biologists begin rewriting the tree of life. Scenario 2. Signal from the stars. A narrow-band radio transmission is detected, clearly artificial, repeating, from a nearby star system. Humanity is stunned. A global protocol for contact is enacted. Decades pass as we try to decode it. Meanwhile, schools, religions, and worldviews shift. A new era of cosmic humility and curiosity begins. Scenario 3. Arrival. A spacecraft, clearly not ours, enters the solar system. It does not land, nor communicate directly. It watches. Then it leaves. Panic and wonder collide. Are they watching? Judging. A new global movement emerges to become worthy of future contact. Scenario 4. We are the ancients. Eons pass. We expand. We find no one. We terraform Mars, seed life on distant worlds, build Dyson spheres. We realize, we were the first. And now, we are the seeders of life, the ancestors of civilizations yet to come. This final scenario is the most awe-inspiring. It turns the question inward. If we find no one else, what responsibility do we bear as the only voice in a silent cosmos? Conclusion. A living universe. As we journey across the stars with our minds and machines, one truth becomes increasingly evident: the universe is not silent. Whether through the molecular whisper of amino acids on distant moons or the structured hum of potential alien signals, there is a growing sense that we are not the only chapter in the book of life, perhaps not even the first, and certainly not the last. Yet in the absence of definitive contact, we are still alone, alone with the question, the hunger, the reach. And maybe that's what defines intelligent life, not just its capacity to survive, but to seek. To look beyond the horizon. To send rovers into the sand of Mars and telescopes into the void. To wonder if a flicker of light in a neighboring system is a cosmic mirror, reflecting our own curiosity. Whether life is common or rare, microbial or majestic, the quest itself reshapes us. It forces us to confront what it means to be alive, to be intelligent, and to be human in a universe that is vast, mysterious, and, just possibly, teeming with life. In the words I carry with me, to seek life in the cosmos is to seek ourselves, writ large across the stars. We are still listening, still searching, still dreaming. And perhaps, somewhere out there, someone is doing the same. Chapter 9. Humanity's Journey to the Stars. The stars have long captured the imagination of humankind, serving as symbols of hope, aspiration, and mystery. From the first ancient civilizations that mapped the constellations to the modern-day space missions that venture beyond our planet, humanity's connection with the cosmos has evolved from mythological wonder to scientific exploration. As we take the next steps into the final frontier, we must ask, what drives us to journey beyond our home world, and what do we seek in the depths of the universe? More than just a pursuit of knowledge, the journey to the stars is a testament to our unyielding curiosity, our longing to expand our horizons, and our desire to understand our place in the cosmos. The birth of a spacefaring species. The origins of humanity's spacefaring ambitions can be traced back to the early 20th century when the dream of reaching the stars began to be articulated not only by scientists and engineers but by the world's greatest thinkers. Figures such as Konstantin Tsiolkovsky, Wernher von Braun, and Robert Goddard laid the theoretical and practical foundations for space exploration, proposing rockets capable of reaching the Earth's orbit and beyond. Yet, it wasn't until the mid-20th century that technology caught up with vision. The launch of Sputnik 1 by the Soviet Union in 1957 marked the first human-made object to enter orbit, initiating the space age and bringing the dream of space exploration into reality. The United States and the Soviet Union embarked on a bitter rivalry, each nation seeking to outdo the other with monumental space achievements. But this competition would, ultimately, foster unprecedented advancements in science, engineering, and human exploration. With the successful human spaceflight of Yuri Gagarin in 1961 and the subsequent Apollo missions that culminated in the historic moon landing in 1969, humanity proved that the stars were no longer distant and unreachable. The philosophical implications of space exploration. The exploration of space carries profound philosophical implications. The very act of reaching beyond our planet to explore other celestial bodies compels us to reconsider our place in the universe. For centuries, Earth was believed to be the center of the cosmos, a belief reinforced by religious and cultural ideologies. However, as we've gained the technological capabilities to peer deeper into space, it has become clear that we are not at the center of the universe, nor are we the only life forms. In many ways, space exploration forces us to confront the concept of cosmic humility. The vastness of the universe, the billions of galaxies, stars, and planets, presents a humbling reminder of how insignificant our species is in the grand scale of existence. Yet, this realization doesn't dampen our spirit, rather, it amplifies the drive to explore and understand. Space offers an opportunity to learn about the origins of the universe, the formation of stars and planets, and perhaps, the existence of extraterrestrial life. It opens new frontiers for scientific inquiry, potentially answering some of humanity's oldest questions. What are we? Why are we here? Are we alone in the universe? Additionally, the pursuit of space exploration challenges us to rethink concepts of time and space itself. The vast distances involved in traveling beyond our planet force us to consider the potential limitations of our current understanding of physics. Ideas like faster-than-light travel, time dilation, and the nature of black holes are no longer the domain of science fiction. They are central to the discussions surrounding the future of interstellar exploration. In some ways, space exploration acts as a laboratory for testing and expanding the frontiers of our understanding of reality. Space exploration is a global endeavor. While the early days of space exploration were defined by national competition, today's efforts reflect a broader, more cooperative spirit. The establishment of the International Space Station (ISS) in 1998 marked a significant milestone in international collaboration. In contrast to the Cold War-era space race, the ISS brought together space agencies from the United States, Russia, Japan, Canada, and the European Union to build and operate a permanently inhabited space station. For over 2 decades, astronauts from around the world have lived and worked aboard the ISS, conducting experiments that benefit all of humanity. This spirit of international cooperation extends beyond the ISS. For example, the James Webb Space Telescope, a joint project between NASA, ESA, European Space Agency, and CSA, Canadian Space Agency, promises to revolutionize our understanding of the universe. These multinational collaborations demonstrate that space exploration is not solely the domain of a few superpowers, it is a collective endeavor that requires shared knowledge, resources, and expertise. This collaborative approach has made space exploration more accessible and inclusive, encouraging countries of all sizes to participate in the quest to understand the universe. As humanity continues to push the boundaries of space exploration, the question of how we govern space will become increasingly important. Who owns space? How do we prevent conflict in space? As nations, private corporations, and other stakeholders work to mine asteroids, establish lunar bases, and explore the outer reaches of our solar system, the need for clear, ethical frameworks for space exploration will only grow. International treaties like the Outer Space Treaty, established in 1967, are already in place to promote peaceful exploration, but more work is needed to address emerging challenges such as resource extraction and planetary protection. The age of private space companies. As we enter the 21st century, a new era of space exploration is unfolding, one driven by the rise of private space companies. Historically, space exploration was dominated by government agencies such as NASA, Roscosmos, and the European Space Agency. However, the emergence of companies like SpaceX, Blue Origin, and Rocket Lab is reshaping the landscape of space exploration. SpaceX, founded by Elon Musk in 2002, has been at the forefront of this revolution, with its Falcon rockets and Dragon spacecraft offering affordable and reliable access to space. The company's successes have significantly lowered the cost of launching payloads to orbit, opening the door for new possibilities in satellite deployment, space tourism, and beyond. Perhaps the most ambitious project to date is SpaceX's Starship, a fully reusable spacecraft designed to carry humans to Mars and other destinations in the solar system. SpaceX's vision for the future is not just about space travel, it's about the colonization of other planets and ensuring the long-term survival of humanity. Blue Origin, founded by Amazon's Jeff Bezos, has similarly focused on creating reusable rocket technology. Blue Origin's New Shepard and upcoming New Glenn rockets are designed to carry cargo and passengers into suborbital space, with the goal of making space tourism a viable industry. Blue Origin also shares SpaceX's long-term vision of space colonization, with Bezos proposing that millions of people could one day live in giant space habitats in orbit around Earth. This idea has captivated the imaginations of many, as it suggests a future in which humanity has expanded beyond Earth and into the cosmos. These companies, along with others like Virgin Galactic, Rocket Lab, and Relativity Space, are not only making space more accessible, they are creating an entirely new space economy. In the coming decades, we may see the rise of space industries such as asteroid mining, lunar resource extraction, and even space-based manufacturing. The commercial space industry is positioned to become one of the most lucrative sectors of the global economy, driving innovation, job creation, and the development of new technologies that benefit life on Earth. However, the rapid expansion of the commercial space sector also raises important questions. How do we ensure that space remains accessible to all nations and not just the wealthy corporations? How can we prevent the privatization of space resources from exacerbating inequality or causing harm to the environment? These questions will require careful consideration as we enter this new chapter of space exploration. Mars and the future of human colonization. As we look toward the future, one of the most exciting possibilities is the colonization of Mars. The red planet has long captured the human imagination, and in recent years, Mars has become the focal point of humanity's ambitions beyond Earth. SpaceX's goal of sending humans to Mars by the mid-2020s is a significant step toward making this vision a reality. The challenges involved in sending humans to Mars are immense: long-duration space travel, radiation exposure, and the establishment of a self-sustaining colony are just a few of the obstacles that must be overcome. However, the potential rewards of colonizing Mars are profound. The establishment of a permanent human presence on Mars could serve as a Plan B for humanity in case of catastrophic events on Earth, such as natural disasters or even human-made crises like climate change or nuclear war. Moreover, the process of building a colony on Mars will drive innovation in a wide range of fields, from life support systems and space agriculture to advanced robotics and artificial intelligence. It will also push the boundaries of what is possible in human endurance and resilience. Beyond Mars, the moons of Jupiter and Saturn, such as Europa and Titan, also hold the promise of exploration. Europa, with its subsurface ocean, may harbor life, while Titan, with its dense atmosphere and lakes of methane, presents an entirely new set of challenges and opportunities for exploration. As our technology continues to improve, the outer reaches of the solar system will become increasingly accessible. The dream of interstellar travel. While Mars is currently the next logical destination for human exploration, the ultimate frontier for humanity is the stars themselves. The dream of interstellar travel has captivated writers, scientists, and visionaries for generations. While we currently lack the technology to travel to another star system, advances in propulsion technologies, such as nuclear fusion and the concept of a warp drive, may one day make it possible to travel to the nearest stars, such as Proxima Centauri, which lies just over 4 light-years from Earth. The dream of reaching the stars represents the ultimate expression of human ambition. It is a bold vision of a future where humanity is not confined to the solar system but is instead a spacefaring species, exploring and settling worlds in other star systems. While this goal may seem distant, the pursuit of interstellar travel will push the boundaries of our scientific understanding, our technological capabilities, and our philosophical outlook on life itself. The legacy of humanity's journey to the stars. As we look ahead to the future of space exploration, we must ask, what is the legacy we want to leave behind? The journey to the stars is more than just an endeavor for scientific discovery, it is a journey that will shape the future of our species. It is a chance to demonstrate our collective will to survive, to explore, and to connect with the universe around us. It is an opportunity to build a future where humanity is no longer confined to the Earth but is free to reach for the stars, to build civilizations beyond our planet, and to seek new worlds for future generations. The journey to the stars is a testament to the resilience of the human spirit, a manifestation of our deepest hopes, dreams, and aspirations. And as we continue on this journey, we must remember that space exploration is not just about the science, the technology, or the conquest of new frontiers. It is about us, about humanity's enduring quest to understand the universe and our place within it. In the end, the journey to the stars is not just about the destinations we reach, but about the very act of reaching for them. Chapter 10. The Illusion of Nothingness. The Paradox of Nothingness. Nothingness has been one of the most perplexing and elusive concepts throughout history, engaging both philosophers and scientists alike. It is paradoxical in nature. We are drawn to define what it is, even though it seems to defy definition. The idea of nothingness, of an absence of matter, energy, and even time, remains an enduring enigma. Yet, it is a concept that shapes everything around us, the cosmos, the fabric of space-time, and even the very notion of existence itself. How can nothing truly exist if the universe itself is filled with something? This chapter seeks to explore the illusion of nothingness in the cosmos, examining its meaning, its implications, and how our perceptions of it have evolved. The more we try to uncover its true nature, the more we find that nothingness is far from empty. Whether in the empty spaces of the universe or in the invisible forces that shape the cosmos, what we think of as nothing often reveals hidden complexities. This realization blurs the boundary between what we understand as something and what we perceive as nothing. Philosophical perspectives on nothingness. The concept of nothingness has deep roots in philosophy, where it has been explored through various lenses: existential, metaphysical, and even ethical. Ancient Greek philosophers such as Parmenides and Plato debated the nature of non-being, the very absence of existence. Parmenides argued that nothing could not exist, because to speak of nothing was to create a contradiction. Plato, on the other hand, spoke of a world of forms, where physical reality was only a shadow of a deeper, perfect existence. In more modern times, existential philosophers like Jean-Paul Sartre and Martin Heidegger grappled with nothingness in the context of human existence. Sartre's notion of nothingness was central to his philosophy of freedom, where human beings were confronted with the void of meaning and the responsibility of creating their own purpose. Heidegger, too, saw nothingness as an integral part of human existence, particularly in his exploration of death and the nothing that defines the limits of being. For many philosophers, nothingness is not a mere absence but a source of meaning and contemplation. In existentialism, nothingness is paradoxically what gives rise to life itself. Our awareness of the void forces us to define our own existence. Thus, while we may encounter emptiness, it is never truly empty. It is the space in which our own thoughts, actions, and creations emerge. Scientific views. The quantum vacuum and beyond. In the realm of physics, nothingness has a different connotation. For centuries, science taught that a perfect vacuum, an absolute void, existed in the universe. However, the development of quantum theory revealed that this vacuum is anything but empty. The quantum vacuum is a seething, fluctuating sea of energy, with particles constantly appearing and disappearing. According to the uncertainty principle, there is no such thing as a perfect vacuum because empty space is constantly influenced by quantum fields. Quantum fluctuations mean that what we perceive as nothing is actually filled with an infinite number of virtual particles, popping in and out of existence on incredibly small timescales. This means that nothing, in the quantum sense, is a state of perpetual activity, even in the most seemingly empty regions of space. The quantum vacuum is not a still, lifeless void but a turbulent, energetic backdrop from which all matter and energy can emerge. This understanding of nothingness is a far cry from the old philosophical and intuitive notion of a void devoid of everything. The quantum vacuum challenges our perception of emptiness and invites us to reconsider the very nature of reality itself. Rather than being a passive absence, nothingness in the quantum world is a dynamic force that shapes the universe. The cosmic void. On a larger scale, the concept of nothingness manifests in the cosmic voids, vast regions of space that are almost entirely devoid of matter. These cosmic voids, which make up a significant portion of the universe, contain only a fraction of the galaxies, stars, and other celestial objects that fill the rest of the cosmos. Voids stretch across billions of light years, creating vast expanses of emptiness. Yet, even in these cosmic voids, nothingness is not truly empty. Studies of dark matter and dark energy have revealed that these regions are far from devoid of influence. Dark matter, which makes up about 85% of the universe's matter, exists even in the voids, exerting gravitational forces on the surrounding matter. Furthermore, dark energy, responsible for the accelerated expansion of the universe, permeates every corner of space, including the voids. The cosmic void is an interesting reflection of nothingness, a vast emptiness that challenges our understanding of space itself. What once appeared as a simple absence is now understood as a complex, dynamic region filled with invisible forces. Nothingness, it seems, cannot escape the influence of the unseen, whether in the form of dark matter or dark energy. Even in the most barren stretches of the universe, the fabric of spacetime is still active, suggesting that the void is never truly nothing. The fabric of spacetime, the thin line between nothing and something. When we look at nothingness in the context of spacetime, we encounter an even more profound mystery. Spacetime itself, the very fabric of the universe, is not a static backdrop against which events unfold. It is a dynamic entity that can bend, stretch, and warp in response to mass, energy, and gravity. This curvature is what we perceive as gravity, a force that shapes the behavior of celestial bodies and governs the motions of galaxies and stars. The boundaries between nothing and something become increasingly blurred when we consider how spacetime behaves. A vacuum, or an area of low energy, is still part of the underlying fabric of spacetime, and it responds to the same forces that shape matter. The idea of an empty universe, one where spacetime is entirely flat and unchanging, is more of an abstraction than a physical reality. In truth, spacetime itself is never truly empty. It is a medium through which the most fundamental processes of the universe unfold, whether in the form of gravitational waves or the warping caused by massive objects like black holes. Thus, what we perceive as nothingness, whether it's a cosmic void or a vacuum in quantum mechanics, is always bound by the nature of spacetime itself. The distinction between nothing and something is often a question of perspective. In the universe, even apparent emptiness is never truly devoid of structure or influence. The Big Bang and the origin of the universe. The question of whether the universe emerged from nothing is one of the most profound inquiries of modern cosmology. The Big Bang theory suggests that the universe began from an extremely dense and hot state about 13.8 billion years ago, but what preceded this event, if anything, is still a matter of speculation. Some scientists argue that the Big Bang represented the creation of space and time itself, while others propose that the universe emerged from a quantum fluctuation in a pre-existing void. From a scientific standpoint, the idea of nothing as a precursor to the universe seems increasingly difficult to accept. In quantum mechanics, particles can arise from seemingly nothing due to fluctuations in energy fields, but these fluctuations are governed by the laws of physics. If the universe originated from nothing, it would suggest that these laws themselves emerged from the void, a concept that defies our traditional understanding of cause and effect. In this sense, the Big Bang might not represent the beginning of everything but rather a transition from one state of existence to another. Whether we view the origin of the universe as the emergence of something from nothing or the transformation of one state into another, the question itself challenges our deepest assumptions about reality. Nothingness in black holes, the singularity. Black holes are another place where the concept of nothingness becomes even more profound. At the heart of a black hole lies a point of infinite density called the singularity, where the laws of physics break down, and the fabric of spacetime collapses upon itself. Within this singularity, it is believed that all matter and energy are compressed into an infinitely small space, creating a point where nothing, no matter, no time, can exist as we understand it. The singularity represents the ultimate form of nothingness, a region where space and time cease to have meaning, and the universe's conventional rules no longer apply. In theory, the singularity is a place where all of the universe's mass is concentrated in a single point, creating a state that is both infinitely dense and infinitely small, an existential paradox. However, even within black holes, the notion of nothingness is contested. Recent research in quantum gravity suggests that the singularity might not be a true nothingness, but rather a region where the effects of quantum mechanics and general relativity converge. If quantum theories are correct, the black hole singularity may not represent a point of absolute emptiness but a more complex structure that defies our current understanding. The illusion of nothingness, a changing perspective. As our understanding of the universe deepens, so too does our comprehension of nothingness. We now know that what we once considered empty space is filled with invisible forces, from quantum fluctuations to dark energy. Even the vast cosmic voids, which appeared to be nothing, contain a wealth of unseen phenomena that influence the structure of the universe. The illusion of nothingness, it seems, is just that, an illusion. There is always something, whether it is energy, fields, or unseen forces at work. What we once viewed as the absence of matter is now understood to be a complex, active region of space. The more we probe the depths of the cosmos, the more we uncover that nothingness is not the simple void we once imagined but a landscape rich with hidden phenomena. The end of time and the universe. Looking forward, the concept of nothingness continues to shape our vision of the universe's fate. Theories about the end of the universe, such as the Big Freeze, the Big Crunch, and the Big Rip, suggest various scenarios in which the universe will gradually descend into a state of emptiness. As stars burn out and galaxies drift apart, the universe may eventually approach a state where matter is spread thinly across an ever-expanding void. In such a future, the universe would become a vast, cold, and empty place, filled with the remnants of what once was. However, even in these scenarios, nothingness is never truly nothing. The universe may evolve into a state where it is devoid of recognizable structure, but the underlying fabric of spacetime will persist. Whether in the form of quantum fluctuations or the forces of dark energy, there will always be something, an echo of the cosmos that once was. Embracing the mystery of nothingness. The illusion of nothingness, as we have seen, is a shifting concept. Whether viewed through the lens of philosophy or science, it challenges our assumptions and forces us to reconsider the very nature of existence. While we may never fully grasp the true meaning of nothingness, the search itself enriches our understanding of space, time, and reality. In the end, nothingness is a mirror reflecting our deepest questions about the cosmos. It is not the absence of something but a reminder of the mysteries that lie beyond our comprehension, waiting to be explored. Chapter 11. The Eternal Journey. The notion of the eternal journey is both a scientific exploration of the cosmos and a philosophical reflection on humanity's place within it. It involves the future trajectory of life, the universe's continual expansion, and humanity's ever-evolving quest for meaning and purpose in the vastness of space and time. This chapter delves into these themes, contemplating the endless expanse of the cosmos, humanity's role within it, and the philosophical implications of immortality, transcendence, and the journey through time. The cosmos and its boundless future. The universe, as we understand it today, is not a static entity. It has evolved dramatically since the Big Bang, and it continues to expand at an accelerating rate. Our knowledge of the cosmos is constantly evolving, shaped by our technological advancements, our observations, and our theories. The vastness of space remains one of the most humbling aspects of the universe, one that defies comprehension and challenges our understanding of the fundamental nature of existence. As we look toward the future, there are numerous theories about what will happen to the universe. One such theory is the concept of the heat death, which posits that the universe will ultimately reach a state of maximum entropy, where all energy is evenly distributed and no work can be done. This would represent an end to all activity and life as we understand it. Another possibility is the Big Rip, in which the expansion of the universe accelerates so much that it eventually tears apart galaxies, stars, planets, and even atoms. This would result in a universe devoid of any recognizable structure, a state in which the forces that bind matter together cease to exist. The Big Crunch presents yet another scenario, in which the expansion of the universe reverses itself, causing everything to collapse back into a singularity. Each of these theories represents different end states for the universe, but they share a common theme: the eventual conclusion of the universe's evolution. Despite the uncertainty surrounding the ultimate fate of the cosmos, one thing is clear: the universe is on a journey of its own, one that will continue to unfold long after our time on Earth has passed. The universe itself is eternal, even if its current form is not. Yet, this raises the question: what lies beyond the end of the universe as we know it? Some scientists speculate that the universe could undergo a cyclical process, in which the end of one cosmic phase leads to the birth of another. The idea of a cyclic universe, where the Big Bang and Big Crunch repeat in an endless cycle, offers a glimpse into a form of eternity that transcends individual epochs. This possibility suggests that the journey of the universe may never truly end, even if it continuously reinvents itself. Humanity's role in the eternal journey. For millennia, humans have gazed up at the stars and wondered what lies beyond. Space exploration has been central to this quest for understanding, and with each technological advancement, we have uncovered new facets of the universe. However, the journey is far from complete. Humanity's place in the grand narrative of the cosmos is still being written. Humanity's journey through the cosmos is just beginning. The potential for space travel has advanced significantly in recent years, and we are now on the cusp of a new era of exploration. The possibility of interplanetary travel is no longer a matter of science fiction. Missions to Mars, the establishment of lunar bases, and even the potential for human travel to other star systems could soon be within our reach. The question is, can humanity become an interstellar species? As Earth faces environmental degradation, political instability, and the long-term challenges posed by the Sun's eventual transformation into a red giant, colonizing other planets or star systems becomes an increasingly urgent goal. In fact, some scientists argue that space colonization is not just a possibility, it is a necessity for the survival of humanity. While Earth may continue to be our home for millennia, the idea of establishing humanity on multiple planets could safeguard our species against extinction. Technological developments, such as fusion power, advanced propulsion systems, and artificial intelligence, could make long-distance space travel feasible in the coming centuries. Concepts like the warp drive, although currently theoretical, suggest that faster-than-light travel might one day be possible. The implications of such advancements would be profound, enabling humanity to explore and colonize distant stars. However, space travel on such a scale also presents formidable challenges. The vast distances between stars would require a level of endurance and innovation that we have yet to achieve. Colonies on distant planets would need to be self-sustaining, with technologies that support life over long periods. The psychological and physiological effects of long-term space travel are still not fully understood, and intergenerational voyages could pose significant obstacles. Despite these challenges, the potential for humanity to become an interstellar species represents the ultimate extension of our eternal journey. Just as early explorers ventured into uncharted territories on Earth, so too will future generations venture into the unknown reaches of space. Philosophical implications. The pursuit of immortality. The eternal journey is not only a physical expedition but also a philosophical exploration. It raises profound questions about the nature of life, death, and existence itself. Since the dawn of civilization, humans have sought immortality in various forms, through religion, philosophy, art, and science. The eternal journey touches upon this quest, as the possibility of surviving beyond our physical form confronts our deepest existential fears and desires. In the realm of space exploration, immortality takes on new dimensions. Digital immortality is one potential path forward. Advances in neural uploading and artificial consciousness might one day allow human minds to live on long after our biological bodies have decayed. By digitizing the brain, we could potentially create a form of existence that transcends the physical limitations of our bodies. While still far from realization, such technologies raise important ethical and philosophical questions. If consciousness can be transferred, does the self persist, or does the mind become a mere simulation of the original? The notion of immortality is also tied to humanity's desire for a cosmic legacy. Just as the ancient Egyptians built the pyramids as tombs for their pharaohs, future generations may seek to leave their mark on the cosmos by establishing permanent settlements on distant worlds. Through these endeavors, humanity would ensure that our presence in the universe is not forgotten. In a more abstract sense, the eternal journey is about understanding time itself. Time is both a prison and a liberator. We are bound by time's forward march, but we also seek to transcend it. If humanity could overcome the barriers of time, whether through space travel or through digital immortality, we would not just be defying the physical constraints of the universe but also achieving a form of transcendence that has eluded us for millennia. Cosmic legacy: humanity's influence on the universe. As we venture into the cosmos, the question of legacy becomes central. If humanity succeeds in reaching the stars, what kind of legacy will we leave behind? Will our civilization endure for millions or even billions of years, shaping the future of other worlds? Humanity's legacy will be marked not just by technological achievements, but by the way we interact with the cosmos. Our relationship with the universe will define our place in its vast, ever-expanding narrative. By exploring space, we may discover new forms of life, new civilizations, or entirely new realms of existence. Our ability to build lasting, sustainable colonies on other planets will be a testament to our adaptability and ingenuity. Perhaps humanity's most lasting legacy will not be the physical marks we leave on distant worlds, but the knowledge we acquire. The discovery of life on other planets, the unraveling of the mysteries of dark matter, and the understanding of the true nature of spacetime will resonate across the cosmos, informing the future of intelligent life across the universe. Time, the universe, and eternity. The final aspect of the eternal journey is the relationship between time and the cosmos. Time is the ultimate constant in our understanding of the universe. It governs everything, from the birth and death of stars to the unfolding of cosmic events. But time itself is a mystery. The theory of relativity shows that time is not uniform. It is shaped by gravity and the relative motion of observers. This means that time can stretch, bend, and even slow down depending on one's position in the universe. As we contemplate the future of the universe, we must also ask, will time itself continue to exist as we know it? The end of the universe could signify the end of time, as we understand it. The concept of eternity, as a timeless state of being, may hold the key to understanding our ultimate fate. In some interpretations of cosmology, time itself may be a finite construct, existing only as long as the universe itself does. The end of the universe might also mark the cessation of time, an eternal stillness that defies our understanding. In this version, we've deepened our exploration of humanity's journey through space, examined the philosophical implications of immortality, and considered our potential legacy in the universe. This narrative extends our understanding of the eternal journey, making it a profound reflection not only of the future of the cosmos but of humanity's place within it. The eternal journey is, after all, as much about the quest for knowledge and transcendence as it is about the exploration of time, space, and existence itself. Albert Einstein, architect of spacetime. When we speak of space and time as woven together into a cosmic fabric, bending and stretching under the weight of stars and galaxies, we are speaking the language Albert Einstein gave us. Born in 1879 in Ulm, Germany, Einstein redefined the universe not by adding to the old frameworks, but by daring to imagine entirely new ones. His special theory of relativity, published in 1905, introduced the radical idea that time and space are not fixed and separate entities, but are instead interwoven and dynamic. He showed that time could slow down and distances could contract depending on one's motion through space. Suddenly, the cosmos was not the immutable stage upon which the drama of the universe unfolded. The stage itself could shift and warp. 10 years later, Einstein expanded these ideas into his general theory of relativity, revealing that gravity was not merely a force pulling objects together, as Newton had described. Instead, gravity was the result of massive bodies curving the fabric of spacetime itself. Planets, stars, and black holes carved valleys and hills into this fabric, guiding the paths of everything around them. It was a profound and poetic revelation. Mass and energy told spacetime how to curve, and spacetime told matter how to move. Einstein's equations predicted phenomena so strange they seemed almost fantastical: black holes from which nothing could escape, gravitational waves rippling across the universe, the bending of starlight around massive objects. Decades after his death, these predictions continued to be confirmed by experiments and observations, each discovery reaffirming the breathtaking accuracy of his vision. But Einstein was more than a physicist. He was a philosopher of the cosmos. He sought a universe that was rational, elegant, and understandable, a place where the mysteries of existence could be captured not just by equations, but by the sheer beauty of human thought. Even as he wrestled with the strange implications of quantum mechanics, Einstein remained a voice for a universe governed by deep, underlying simplicity. In the quiet moments of reflection, Einstein often spoke of wonder, a feeling he believed was at the heart of all true science. In his own words, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and all science." Albert Einstein reshaped not only our understanding of gravity, but our very sense of reality. Through his genius, the universe became a dynamic, living fabric, a grand, ever-evolving tapestry stretching across the infinite horizon of existence. As we explore the cosmos, we walk paths first illuminated by the light of his mind. Stephan Hawking. A mind beyond time and space. In the story of humanity's quest to understand the universe, few figures stand as brightly as Stephan Hawking. Born on January 8, 1942, exactly 300 years after the death of Galileo, Hawking's life seemed destined to be interwoven with the stars. Despite being diagnosed with a rare motor neuron disease at the age of 21 and given only a few years to live, he defied all odds, transforming personal adversity into a lifelong journey through the cosmos. Hawking's greatest contributions reshaped our understanding of black holes and the very fabric of spacetime. His groundbreaking proposal, that black holes are not completely black but instead emit radiation, now famously known as Hawking radiation, shook the foundations of theoretical physics. This revelation united principles of quantum mechanics, thermodynamics, and general relativity, illuminating a deeper layer of reality where the immense gravity of a black hole could not entirely prevent the escape of energy. Beyond the technical brilliance, Hawking's vision dared to ask the grandest questions: how did the universe begin? What happens at the edge of time? Can we know the mind of God? In his best-selling book A Brief History of Time, he made the mysteries of the cosmos accessible to millions. He refused to let the complexity of the universe be locked away in academic journals. He believed that everyone had the right to wonder, to imagine, and to understand. Hawking also explored the concept of a no-boundary universe, suggesting that the cosmos might have no singular starting point, no sharp moment of creation, but rather a smooth, timeless transition. In doing so, he changed the way we think not only about beginnings but also about existence itself. His body may have been confined to a wheelchair, but his mind traveled farther than most humans ever dared. Through black holes, singularities, and the infinite stretches of spacetime, Hawking taught us that true exploration knows no physical limits. Stephen Hawking's life was more than a series of scientific achievements, it was a testament to the power of human spirit. He showed us that intelligence, courage, and curiosity could break through even the cruelest constraints of fate. His legacy lives not just in equations or discoveries, but in the endless yearning of humanity to reach beyond the stars and grasp the nature of existence itself. As we journey through space and time, Hawking's voice, synthesized but unmistakably human, echoes in our minds. Remember to look up at the stars and not down at your feet. Glossary. Black hole. A region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. It is formed when a massive star collapses under its own gravity. Cosmic microwave background, CMB. The faint glow of radiation that fills the universe, a remnant of the Big Bang. It provides evidence for the early universe's conditions. Dark matter. A form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Dark energy. A mysterious force driving the accelerated expansion of the universe. It is thought to make up about 68% of the total energy content of the universe. Event horizon. The boundary surrounding a black hole beyond which nothing can escape. Once something crosses this point, it is drawn into the black hole. General relativity. Einstein's theory that describes gravity as a result of the curvature of spacetime caused by the mass and energy of objects. It replaced Newton's law of universal gravitation. Gravitational waves. Ripples in spacetime caused by the acceleration of massive objects, predicted by Einstein and detected in recent years by observatories like LIGO. Horizon. The limit of what can be observed in the universe due to the finite speed of light. Beyond this limit, objects are too far away for light to reach us within the age of the universe. Multiverse. The hypothetical set of multiple, possibly infinite, universes, including the one that we inhabit. These universes may have different physical constants and laws. Neutron star. A compact, dense remnant of a massive star that has exploded in a supernova. It is primarily composed of neutrons and has a very strong gravitational field. Quantum mechanics. A branch of physics dealing with phenomena at very small scales, where particles exhibit behaviors such as wave-particle duality and uncertainty. Redshift. The shift of light to longer wavelengths as objects in space, such as galaxies, move away from the observer. It is evidence of the expanding universe. Singularity. The point at the center of a black hole where the curvature of spacetime becomes infinite, and known physical laws break down. Spacetime. The four-dimensional continuum that combines the three dimensions of space with the dimension of time. It is the framework in which events and objects are described in relativity theory. Supernova. The explosion of a star at the end of its life cycle. It releases a tremendous amount of energy and can briefly outshine an entire galaxy. Time dilation. A phenomenon predicted by relativity, where time passes at different rates depending on the speed or gravitational field in which an observer is located. Wormhole. A theoretical tunnel-like structure in spacetime that could connect distant parts of the universe, potentially allowing for faster-than-light travel. Zero-point energy. The lowest possible energy that a quantum mechanical system can have, even at absolute zero. It represents the energy of empty space itself. About the author. Ayoub Lafriki is a visionary thinker, endurance runner, and explorer of the cosmos. His passion for space, time, and existence drives his work, blending scientific insight with a deep sense of wonder. Through his writing, Lafriki seeks to inspire others to look beyond the horizon, question the unknown, and embrace the endless journey of discovery.